Hi, good morning. Good morning, sir. Sir, shall we start?
Hello, yeah, Prince.
Yeah. So, hi, good morning, everyone. So, on behalf of Chipin team, I myself, Prince Sani, welcome you all to this 3 days technical workshop on a Tcad tool by Synopsys team under C2S program hosted by Chipin Center, CDEC Bangalore. So, today is the day 3 of the workshop. So, today we will be covering simulating DC transfer and output characteristics of MOSFET, simulating AC characteristics of a MOSFET, and post session we will be having a Q&A session as well. So again, from Synopsys team, we have Sushant Mittal sir, Sameer sir, and Narendra sir. We warmly welcome you, sir, today's session. So now I would like to request Narendra sir from Synopsys team to take over the session. Over to you, sir.
Thank you, Prince. So, good morning, everybody. So, today we are going to see device simulation using CentOS device, which we also call S device. So yesterday this CentOS process part was covered by Sushant. So at the end of the day, end of the session, we were able to create a structure file, TDR file. Now we are going to perform electrical simulations and derive terminal characteristics by performing simulations in S-device. So we will be using today S-device.
Narendra, can you go full screen?
Yeah. I just wanted to change the screen. That's why. So before moving forward, let's yesterday actually Sushant told you how to get started with SWB, but still I will request everybody that please try to log in into your accounts and try to open the SW window. So that as we go along during the session, we can also have hands-on. Yeah, so outline for today's session is we will be seeing the device simulation flow within CentOS Workbench, and we'll perform device simulation using S-device tool. We will also see what are the simulation steps. Then equilibrium simulation without biasing the contacts. Then we will see the IV characteristics, transfer as well as output characteristics. And finally, at the end of the session, we will see how to simulate AC and transient characteristics. In AC, we will mainly focus upon small signal AC analysis. So we had on the first day we had seen the layout of SWB. So this was our tool flow which we had discussed. So yesterday Sushant produced a device structure using a CentOS process, and we are here. Our device is ready. So now we will call that device within S-device tool and will perform this IV simulations, and then we will see results within S-visual. Whatever electrical parameters we will extract, that will be seen to the rightmost side of the table. So first, so in the tool flow, the first part is structure generation, which we saw yesterday. Today we are seeing device simulations. We will see we will visualize various types of fields which will be calculated during this device simulation. Then terminal characteristics will also extract device parameters. So this is just a structure or TDR generated structure of your device, where net active concentration means doping and electrostatic potential is being shown. This is your IV characteristic. So we will see this. So basically, what is a device simulation? So Centauros device simulates electrical, thermal, optical properties of semiconductor device, either for a single device or multiple devices connected within a circuit that we will call that is mixed mode, which we will see. So then thermal characteristics, I mean, means IV characteristics and means which are charges which are computed within the device. They are calculated using some physical device equations, and those equations govern the carrier density and continuity, means transport mechanism. So we'll touch upon those things. So basically what we are doing in the Tcad, within Centauros Tcad, we are trying to replicate the real device. So we are trying to mimic as closely as possible its physical properties. And in a sense, we are creating a virtual device, and we will be characterizing it in a virtual environment, as we do for real devices and we measure its experimentally measure its IV characteristics. Similarly, we in this virtual environment within Tcad, we will be measuring IV characteristics, CV characteristics, and we'll try to mimic as closely as possible the real device. So this is just a brief overview of what of the capabilities of Centauros device, what all we are able to perform. So basically we acquire data, experimental data from some external vendors, and then we try to calibrate our models to match the experimental data, and that is how our models are generated within edge device. Then there are various kinds of models which help us to simulate the real device properties, like drift. So for transport, we have drift diffusion, thermodynamic model, hydrodynamic model, and Monte Carlo, etc. Then we can also we also simulate the stress which is induced within the device. Means for example, as an example, for suppose within silicon MOSFET, we usually try to increase hole mobility by means by generating stress by incorporating germanium within the source drain pockets. Then we also have means um, various kinds of transport mechanisms like tunneling mechanisms, trap assessors tunneling, which help us simulate leakage through the gate stacks, or your current through reverse bias current through PN junction diodes. So for those, we have tunneling mechanisms wherever it's applicable. Then we also have models like hot carrier injection. Then apart from silicon, we the Centauros device is capable of means accurately simulating other materials like the 3,5 materials or 3 nitride materials, silicon carbide materials. We have nicely calibrated models for them. So radiation effects are also possible to simulate in this, as well as optical optical generation mechanisms for means like CMOS image sensors, photo detectors, then different kinds of means photo generation mechanisms like ray tracing, FDTD, etc. Means these are the vast capabilities of Tcad to simulate various kinds of real phenomena which is happening within the device. So as we discussed, so 1D, 2D, 3D device structures are possible to simulate within this Tcad frame, and electrical, thermal, and optical characteristics are simulated. Again, along with silicon, we also simulate different kinds of material systems, including wide band gap materials. Then DC, AC, and transient characteristics are simulated, and we have mixed mode simulations. For example, here means this is a single device simulation which will start with. Then we will also see means a mixed mode simulation. We're using a single device, and with other compact models included. Then we can also see, we will also see that we can use multiple devices generated within CentOS, or instances of the same device, multiple instances of the same device, to form a complex circuit to perform mixed mode simulations. So these are just a few examples of the terminal characteristics, which, for example, output characteristics, then transfer characteristics. So this is this comes on our DC analysis. So we also have breakdown analysis. So and as well as transient. So AC, like, means as we are going to see today, we'll see small signal AC analysis. So this is capacitance versus gate voltage, and this is again means threshold voltage roll-off is being shown here. So these all means characteristics are captured nicely, accurately within CentOS. Along with that, we also perform RF simulations. Then we also this tool is capable of performing noise simulations, extracting device figures of merits, and then noise spectral densities. So that we saw the device is this CentOS Tcad tool is quite capable of simulating or mimicking different characteristics of a real device. So what actually happens means how these phenomena are being captured within the device. So basically there are some physics-based equations which govern the equations which govern the carrier motion or carrier state, I would say, means within the device. So these two are our base means fundamental equations, I would say. The Poisson equation. The Poisson equation relates the electrostatic potential and charge within the device. So from that you get the profile for potential, and then from there you get means you can go forward calculating energies, the electric fields. Then continuity equation, solution of continuity equation gives you information about carrier densities. So these equations are solved in a coupled manner within the device to get to eventually get self-consistent solutions for potential, charge densities. So as I said, the solution of potential Poisson equation provides you electrostatic potential. Then current solution of continuity equation finally yields the carrier concentrations. So I would just touch upon the different terms in this. So this is actually divergence of electric field displacement, which is equals to volume charge density. So, and within the on the right hand side, the different terms are your this electronic charge Q, then hole density, electron density, donor dopant density, and acceptor dopant density. This is your charge related to traps. So this everything is forming your charge per unit volume of the Poisson's equation. And within the continuity equation, this is your electron current density and its divergence, and this is your rate of change of electron charge per unit time, and then that equals to this current means recombination generation, net recombination generation current, R minus J. So similarly, the equations are defined for holes. So the equations which I showed you, these are right now in analytical form, but what CentOS device does is means those equations are solved in discretized manner. Means they are your device domain is discretized into several nodes, and carrier information are calculated at each node. So here I'm just giving you a rough means a rough portrayal of how discretization looks like. So your continuum spatial domain is discretized into a mesh, and on the mesh nodes or elements. So here I will talk about mesh nodes. So for example, Poisson's equation. Let's take an example, Poisson equals. So Poisson's equation will be solved. So how is it solved? So for each node, this equation will be solved. So for example, if I want to calculate the potential at this central node, so that potential depends upon the potentials on its adjacent nodes as well, which is governed by this equation. This equation comes after means here I have used finite central difference scheme to discretize that equation, or to take means to convert the analytical equation into difference equation. So, and here we can see, means if we make the element size delta x delta y equal, and if we assume that we are for the moment means solving this Poisson's equation is within the charge neutral region, making it this 0 though. So if we rearrange this though, so we can see that it's actually Poisson's equation in a sense solves for potential by taking average of the adjacent 4 points. When you will do the maths and manipulations, you will see that this psi I of j will become average of these adjacent 4 potentials at the adjacent nodes. So this is just a general, I'm giving a general example how discretization of the equation, for example, Poisson equation, is solved. So this thing will be solved iteratively till convergence. Means this thing is solved at all the nodes and iteratively to get convergence. We'll see that. We'll discuss upon that. Then, so this is how continuum domain is discretized, and then after the solution, converge solution means successfully the solution is obtained. So this kind of graph, electrostatic potential field graph is obtained. So as I said, means you discretize your simulation domain. So meshes are created, nodes are created, and so mathematical equations are solved on the nodes, and then finally you get your electrical characteristics. So central device uses box discretization to discretize the partial differential equations. So simulation steps. So yesterday the device structure was generated using Centros process. So, and the final output of means the TDR file we are going to call within the Centros device is of the form _fps.tdr. This acronym is related to the devices generated device generator from the S process tool. Then apart from the structure, we also need models. Means that will govern various physical equations. So we also need to incorporate model parameters. Then we can also feed external parameter files as well, physical model interfaces through physical model interfaces or compact model interfaces. So we can also feed additional model informations also to the S device. So finally, when all the information is input to S device, then it will yield the output in the form of terminal characteristics, which are stored in .plt file. Then field values, which will be stored in des_des.tdr files. Then also we can also store these AC results of AC analysis in separate file, and then a log file is generated, which gives an overall flow of the simulation, how the simulation went. Then the results can be finally visualized using SVisual. So now, so what are the device simulation steps? So we will specify inputs in the form of structure, and it will contain information regarding geometry, region, materials, contact, dopings. Then along with the structure, we will define different models which will be used to solve the equations, as well as we will also feed material parameters through .par file. Then we will define boundary conditions like biasing conditions, temperature conditions to simulate the device. Then we will also include what are the different types of field values we want to plot within the structure that we can additionally specify within the plot section of the device. Then we will also set numerical settings that will be used to run the simulation. So those settings will be used to solve the semiconductor equations. And in the solve section, will ramp different means device parameters, like we will ramp the contact voltages, or we can ramp parameters like frequency, temperature, or other material parameters. So after we input all these things, then when we finally run the sdevice command file, then these equations will be solved and the results will be saved. Then we can analyze those results in SVisual. For example, for TDR files, we can have contour plots, vector plots. Then for BLT files, we will have electrical characteristics, and then additionally we can also extract electrical parameters using extraction libraries. So now, what does this means command file look like actually? Centralized device command. So this is the command file contains various sections. So like the file section where we define the input file was, for example, what the input TDR file we want to give. Then we define output files like current files, plot files. Then in the electrode section, we will define so whatever contacts we had initially defined during the structure generation. So we will then attach electrodes. So it means now we will define those contacts here in the electrode section. Then we can also, for temperature dependent simulations, we will also additionally define thermode section. Then in the physics section, we will define various physical models, and parameters related to those models will be defined in the .par file. Then in the plot section, we will define whatever fields we need to finally see in the output.tdr file that will be specified in the plot section. So then this current plot is an additional feature to this .plt file, where we can actually store the additional information within the device. Additionally to the current file, in addition to whatever IV currents is being generated. So that can be done using current plot section. So, and then in the math, then we have math section, which defines various numerical methods or strategies which will be used to solve the equations. Then in the solve section, we will ramp the which is electrode voltages, currents, or charges, and other parameters. The type of depending upon what simulation we want to do. So these sections, which I highlighted, they can be placed in a random manner. Means sequencing is not very important here, but within the solve section, inside the solve section, sequencing is important. That matters. So now for device definition, for single device definition, these things are mandatory: file section, electrode section, physics section. So these things, these two things form your simulation results, and this is where your partial differential equations will be solved, and other solved and numeric parameters defined. So here I am showing you the input of the command file. So this is. So at this moment, I would like to pause, and I would like to request you that can you please open SWB in your terminals. So you can also have a look at this simultaneously at your end also. So for example, I am in my home folder. So when I'm opening my SWB. Yeah. So please respond. Means if people can respond in the chat that. So hello.
You're audible, Narendra.
Yeah.
Yes.
So when you open this your CentOS workbench, so and as I had discussed on the
Narendra,
first, yes,
Narendra, there is a
yeah.
request. Can you increase the font size? CentOS Workbench. Go to edit.
Yeah.
It went in the. It's on the top.
Yeah. So
Make it like 11 or 12. Like.
is it better or should I increase it further?
Apply.
Yeah, applied.
Save it. I think it is better now.
Okay.
Also change in the table. View table options.
So it's 13.
You make it 14. 13 is already good. Make it 14.
Okay.
Thank you, Narendra.
Yeah, Sushan, thank you. So what I'm saying is that if you are able to means open SWB on your terminals and add as I had discussed on the first day, that means you need to copy this .zzp file which was shared with you in your DB directory. So when you open this, so this is how your SWB will look like. So what I'm showing right now is these command files. So these are the command files which I am presently showing you in the PPT. Okay. So we'll just quickly go through, means as I said, means as we discussed various in the file section we have different files like the input file. So we also saw this referencing scheme that this will as Samir has said, this will call the means previous TDR file from the previous node, previous real node, simulated real node. Then for output file, again we are giving names in the terms of reference. We are not using hard-coded output names. So when this will be finally pre-processed, then these names will be replaced by that node number and underscore des .tdr files, like that. For each particular node, this will be replaced by that node number underscore acronym dot extension in this format. This is the electrode section. So we have defined means voltage boundary conditions for all the electrodes. And for the gate electrode, we are defining this minus 0.55. We'll see this later. What is this? So in the physics section, we have to define different physical models. And this is in the plot section, we will be defining different field entities which we want to finally plot in the output TDR file. This is the current plot file which will additionally generate information into the plot file, PLT file. So for IDVG means simulation which we'll be doing. So this is the structure of the solve section, where first we will first set drain voltage at some voltage, and then we will bias ramp the gate voltage. And for IDVD case, we will first set the gate voltage at some predefined value, and then we will ramp the drain voltage. So some syntaxing in the means which is followed within the command file. So for comments, you use this star or hash. Then there are some predefined keywords like this grid, parameter, current. So these are predefined keywords. They are case insensitive, but they will means they are known to the command means edge device command file. Then strings are encoded in double quotes. Then we have numbers in the form of integers or floating point numbers. Then vectors, for 1D vectors, we just have one dimensions. For 2D, we define these 2 dimensions in brackets, around brackets. Then and these are the different assignments. So this assignment is will make sense when we'll see this in gedit. So how highlighting changes within gedit editor. Then we can also give means assign values by using string this lists. So lists. So these are the form of lists. So we can delimit them in round brackets or in curly brackets. So for example, this is here we are defining some voltage as a means. So this is actually for for transient thing. Transient simulation means voltage at 0 second, voltage at 2e minus 8 seconds. So these are some of the complexes ways of defining of assigning values to variables using lists. So now, so this input file we already discussed. So this is the comment. Then this @TDR. So this is the @. So this is here a typo is there @. So that will call the previously saved TDR file. Then this parameter will call for the parameter file. Then these are all. This is for whatever you say using whatever you save using current will be stored. The terminal characteristics will be stored, and .plt file will be generated. So everything means all these will be replaced by node specific files. Node, for example, n5 underscore n5 underscore des.plt, that kind of thing. So this is field data, this is log file. So this is the device structure which is input to the edge device. Then after simulating, we get this terminal characteristics. So different various acronyms and extensions are specific to various tools. For edge device command file, the command file is, so this is attached, underscore ds.cmd is attached. So this file gives input for device simulation. Then for structure file, if the structure is generated from S process, then that will have this this thing will be attached. So the underscore FPS stands for the structure generated from S process. Then means also mesh file is also generated underscore msh.tdr. So these files contain means structure and device structure related information like shape, materials, dopings, contacts, etc. Then .par file is a parameter file which will define parameters for various physical models which will be used to calculate the equations, physical equations. Then This is the SAV file which is used to take snapshots during at different bias or different states of the device during whenever, for example, if we are ramping bias, then at different bias points we can take snapshots of the device, and that these snapshots can be again called back later to continue, means to again simulate over them. These files can be again used to continue simulations. Then plot file underscore ds.area. So the file which is generated from the device simulation. So its extension is underscore ds.tdr. So it will show the various field entities which are which have been simulated. Then this underscore ds.plt and underscore ds.log. This ds acronym is related to whatever files are generated from your S device. PLT is for terminal characteristics, log will simulation log. It will give information about simulation flow. So this is how means CentOS device tool is being implemented within SWB. So, and this is how your experiment is being generated. So as we have already discussed that if we pre-process, for example, if I pre-process this node file, this file. So after pre-processing, so the whatever file names which we have given in terms of references, that will be replaced by node specific files. So for example, here I'm discussing of node 3. If I pre-process this, so these are the various files will be generated for that particular node, and they will be further used in the simulation. So basically, pre-processing replaces your variables with values. So these are your variables, and they are being replaced by these values. In this case, so for N4, it will be when we will pre-process files related to N4, then this will be N4 underscore ds.plt. And here your grid file. This is N1 underscore FPS. So this is this SDevice file is calling the structure file which was generated from previous real node. So while these node referencing nodes refer to real nodes, this is a virtual node which is shown by the sky blue color. So that's why n1 underscore fps.tdr is being called here in this input file section. So we are using referencing to name the files. We are not using hard-coded names. So what is the benefit of using this referencing? So that same file, same command file, which includes this file section, for example, in this form, same command file is used for this as well, but it will generate some files with some other names for different nodes. Hence, this referencing is useful. Now, electrical boundary conditions. So electrode section. So file section is over. Now electrode section. So in the electrode section, we define electrical boundary conditions for the simulations, and by default our contacts are assumed ohmic contacts. We can also define Schottky contacts. So boundary conditions can be defined in terms of voltage, which is the default. You can also define current boundary condition, charge boundary conditions. This is a typical example. So since the S-device structure needs to communicate with other circuit nodes as well. So it internally assumes or implicitly assumes a contact resistance for its contacts as this 1 milliohm, but we can set the contact resistance for electrodes or contacts of the device. We can set it explicitly. And for 2D structures, the unit of resistance is ohm micrometer. So here are your contacts which were defined in the structure file when you had generated your structure using S process. So in the electrode section again, so we said that we will come back to this. So this barrier is equal to minus 0.55. So this is what this is saying is that the Fermi level at the gate side is difference of the Fermi level at the gate side and compared with compared with the intrinsic Fermi level within the semiconductor side, that difference is minus 0.55 volts. So that means that in this case the work function at the gate side is lower compared to the work function referenced to mid gap energy level within the semiconductor by 0.55 electron volts. So this helps to set the potential at the gate side. And how this comes means how this becomes helpful. For example, when we have polysilicon gates, then when we define this barrier in this form, then it automatically takes this means this contact potential is automatically set for this polysilicon gate, and we can remove that gate. So for this syntaxing is helpful for defining this potentials as polysilicon gate with so when we are not explicitly defining the polysilicon region, we have removed it. For metal semiconductor junctions, for example, metal deposit on a semiconductor, we can we directly define this. We can define work function, metal work function. In this case, this 5 electron volts. So in addition to this voltage boundary conditions, we can also give time dependent. So these are fixed boundary conditions. We can also give time dependent boundary conditions at the electrodes. For example, we can define 5 volts at 0 seconds and 10 volts at, for example, 1 microsecond. So this is also possible. Then another way for defining Schottky contacts is you can just specify barrier. So this now in this case, this says that the Schottky barrier height at the metal semiconductor junction is 0.78 electron volts. So you can also specify in this form, means give the metal work function, or you can just specify the barrier height at the metal semiconductor junction. So you can also specify this area factor. Area factor, for example, by default, the dimension, for example, in the 2D case, the dimension in the Z direction is 1 micron. So if you define an area factor, suppose X, then that will get multiplied with whatever currents you are. So that will actually mimic a 3D device with I would say dimension in the Z direction as X. But for that case, for this thing to be valid, it's important that we have, means the device is uniform in that direction. The structure is uniform in that direction. So we can also define series resistance within the electrode section. And as I said, we can define current and charge boundary conditions. We can also define surface recombination velocities within the for the electrodes in this in the electrode section. For example, here it's electron recombination velocity or hole recombination velocity. These things can be defined within the electrode section. Now, so what are the different ingredients which are being used to model this, to model the physical phenomena? So we are defining the. So now we are specifically talking whatever is inside the S-device command file. So we are giving the boundary conditions. We are defining dielectric properties. Then we are. So again, this band gap and carrier statistics models. We are defining this for the particular structure. We are defining models like mobility models, recombination generation models. Everything is being defined within the S-device command file. Then hello, yeah. So when everything is fed into the solver, then your basic semiconductor equations will be solved to generate the output. So now as we discussed, so these are the basic equations. So drift diffusion equations and this Poisson equation, which are being solved in discretized form within the device. And so this so basically this thing goes as your input. So how does it look in this form? So structure, whatever we generated in this process, like, and it contain information about region, boundaries, contacts. So we saw that everything these things went into the these contacts went into the electrode section. So these informations are fed into the SDVice command file. So from here it takes this, for example, doping information, permittivity information, band gap model information. So it will use band gap models. Then it is also using carrier density, whatever information was generated initially in the structure file, then trap information. Then here we are additionally specifying various models. So these things, these inputs, and then these things set within the command file, then we are ready for SDVice simulation. So physical models and model parameters, as we already said. So we define physical models within the model section of the command file, and the parameters which govern those models, they are defined within the parameter file. For example, if we are defining constant mobility model for the carriers, then parameters related to that model are defined within the parameter file. So so this actually this mobility is governed by some equation, or that equation we are referring as a model, and for that we have some coefficients. Those coefficients values can be we can change those values. We can give our own values in the parameter file. So so some models are active by default itself. Even, for example, if you do not specify mobility model for the carriers, and if you just run your simulation, then this SDY solver will automatically use this constant mobility model, which depends means in which the carrier mobility degradation depends on phonon scattering. So even if you do not define, your simulation will run. But when you want to mimic your experiments as closely as possible, you need to you need to include models. So how do we define the physical models within the physics section? So this one thing is that we can globally define the models. So those will be wherever they are applicable within the device, they will be applied. Otherwise, we can just give models, physical models. We can define particular regions, or in particular materials, or at region interfaces, or at material interfaces. But be sure that if you define physical models then using some qualifier. So you do not repeat that. You define that only once. So use only one physics section statement per qualifier. For example, if you are defining for example, oxide and semiconductor interface, you have already defined a physics model, then again do not see this. So do not repeat that statement, otherwise the most recent will be overwritten over that. So don't specify it only once. Then in the physics section, what are the different models? We can incorporate different models. So this is just an example where band gap narrowing will be taken into account. So if your device contains very high doping densities, or if you are operating at a very high temperatures, then your band gap shrinks. So in that case, so that physical phenomenon should be taken into account. So we have different models for those. For example, here here we have shown this band gap narrowing, where a slot boom model is being used. For mobility also, we can specify different models and recombination. So this, so as we know that this carrier density, intrinsic density depends upon your band gap exponentially on the band gap. As band gap increases, intrinsic density decreases. For silicon, I think we have around 10 to the power 10 intrinsic density, but for wide band gap semiconductors like gallium nitride, it goes 10 to the power minus 6 minus. I mean, it's negligible. So intrinsic carrier density depends on your band gap. So band gap narrowing means it is important that we correctly incorporate band gap narrowing in our simulations. This is band gap narrowing is usually not included for 3.5 materials because calibrated data is not unavailable for those. So one is so regarding your carrier densities, so you can calculate your carrier densities either using Boltzmann statistics, so which is just a simple exponential dependence upon the difference of EC and EF or EF and EI, or if you have very high carrier concentrations in some particular regions, for example, at the oxide semiconductor interface under inversion or in accumulation bias regions. In that case, your Fermi level goes very close to the conduction band or very close to the valence band, where your Boltzmann statistics are not no more applicable. So for more accurate calculations, you can use Fermi Dirac statistics. Then if you are dopant, so usually our dopant and activation energy levels, for example, donor energy levels, acceptor energy levels, are very close to the conduction and valence bands respectively. So usually in complete ionization, usually we see almost complete ionization. But if you are simulating at very low temperatures, or if the energy levels of our introduced dopants are quite distant from the band edges, then we need to also take into account in complete ionization. Then regarding band gap narrowing, as I said, if you have very high doping concentrations, then your band gap narrows, and that should be taken into account. So now if there is stress within the device, then deformation potential should also be taken into account. Then there are also quantum mechanical models as well. So for example, in the case of very strong inversion or very strong, for example, in very strong inversion itself, so our normal assumption of that we have effective conduction band density of states lying at conduction band edge is no more valid, since our energy levels will shift. So in that case, the correct calculation of the band or energy levels can be done by quantum mechanical models. Then in the physics, we have these are the different models which are being defined within the physics section. Again, for a particular region, for a specific region, we are defining strain model in terms of piezo. So this is means an example of band gap changing as a function of temperature, and also this band gap narrowing due to this doping is also taken into account. So basically your EG effective is EG function of temperature as well as EG function of doping with some this offset, constant offset. Then this is your chi is your affinity. So as your band gap will change, your affinity will also change. This is taken into account by this equation. So this is how temperature dependence is taken into account, and this EG par is some reference temperature where these parameters were calibrated. So that is that reference temperature is your T par. So this is how band gap dependence of temperature and doping is taken into account within the model. So there are different kinds of band gap narrowing models. So by default, this is Bennett-Wilson model is activated. So we can also use these other kinds of models. So we have to change a model from default, we need to explicitly define it within the physics section. So for example, here now effective inducing density will be calculated from band gap narrowing model, and using this keyword, these keywords can be anything from here. Then to switch off that default model, you just, for example, if you don't want to include band gap narrowing, as we said, for 3.5 material systems, then we can just specify no band gap narrowing. So now this is how your parameter file looks like. So in the physics section, we defined the model. Now in the parameter file, so parameter file contains various sections. Like in the band gap section, you can define different coefficients which will be used in these equations. These equations are our models. So these coefficients we define in the parameter file will be used in the models. This is again an example of effective density of states calculation. So I'm just showing you the formula 2, where if density of states, conduction band density of states as a function of temperature is defined in terms of density of states at room temperature. And also this effective electron mass is calculated in this form, same for holes. And these parameters, for example, NC at 300 Kelvin or NV at 300 Kelvin can be defined in the parameter file. Now, so by default, we saw that constant mobility model is activated, but the actual mobility which actually goes, or which actually governs the mechanism is quite degraded compared to the ideal. Ideal means constant mobility. So the mobility degradation must also taken into account. So in the bulk case, where the carriers, electrons and holes, are not being interacted by other external factors, then only your temperature, lattice temperature, is the factor which will degrade their mobility due to means phonon, lattice phonons. So, but as we, for example, as we are simulating a MOSFET structure, then in that case, our carriers flow very close to the oxide semiconductor interface. Then in that case, degradation in mobility due to interface should also be taken into account. So for those different models are available to take different kinds of scattering of carriers due to impurities and due to surface roughness and due to carrier scattering, then mechanical state. These various types of effects which degrade the model mobility are taken into account. And your net effective mobility is kind of this, follows Matt-Hyson's law. So net will be always lower than these individuals. So as you said, means if nothing is defined, then no low field mobility is defined by default. So for bulk, constant mobility is defined by default. Then if we have, so to take into account this Coulombic scattering due to dopant ions, means electrons getting scattered due to Coulomb attraction, repulsive or attractive, both. So that will be taken into account by using doping dependent mobility models. Then so our MOSFET is our default doping dependence model. So we can also change, that can also be changed by giving the corresponding keyword. For example, we can also use Aurora model. Then we also have this unified model, which takes means various things into account, like carrier scattering, then mole fraction dependent. So this Phillips unified mobility model, for example, takes is a model which takes this phenomena into account. So this is we discussed, means carrier scattering due to Coulomb attractive or repulsive forces of the dopants. So that is taken into account by dopant dependence. For interface, where carrier motion is happening near the interface, then interface effects must also taken into account. For example, in our MOSFET case, we first bias the gate. to form a channel. So electrons are very close to the oxide semiconductor interface in that case, and our carrier motion or current flows from source to drain. So in that case, the transverse electric field from emanating from the gate and reaching to the channel carriers will degrade their mobility in the parallel direction, parallel in the sense source to drain. So that thing must be taken into account. So that we'll take into account by using E normal. So this is how means when interfaces are also playing a role within the carrier for carrier motion within the device, then correspondingly we should also incorporate means appropriate models for those. Then we have high field saturation means so usually for low fields we have velocity is equals to mu into E, where we assume that mobility is constant, and then our carrier drift velocity goes on increasing with the electric field, but that assumption is only valid till for low field values, because when the field in the transport direction becomes very high, then in that case your mobility no more remains constant, it degrades. Then that, and due to that, the product of mobility and field almost becomes constant, and your drift velocity saturates. This phenomena should also be taken into account. So we have high field saturation models for those. So for high field saturation models, we also have driving forces as well. Means what is driving the motion of the carriers. So for example, for the high field saturation, we can also define the driving force like gradient in Fermi level or the electric field. So those options are also available for us. Then we have recombination generation models as well. So recombination model, SRH recombination model. So so SRH will mainly take into account this carrier trapping, detrapping with respect to. So this is localized at a particular position within the device. Traps interacting with band edges, conduction band and valence band edges. So this recombination model, SRH recombination, takes into account. So now, if this SRH, either we can use the doping dependent lifetimes in the SRH model, or we can use a constant lifetimes. Means, for example, if with increasing doping, so basically your lifetime of carriers within the device depends upon inversely depends upon the trap concentration. So, but it may so happen that means so additional traps or additional defects may be generated. Means your lifetime might degrade at higher doping values for carriers. So doping dependent. So SRH can also be doping dependent, and that should also be taken into account. So we can include this model. Then in the case of high energetic particles, when recombining from valence band to conduction band and imparting their energy to the third particles, then Auger recombination models can also. So this is can also be included. So for very high doping conditions, and this should be included. And then semiconductor equations and ramps. So again, these are the semiconductor equations which will be solved. Now, so for electron, so when we specify electron in the solve section, it will solve for electron continuity and it will yield electron density. Similarly for holes, we will get hole density from the continuity equation, and the Poisson will give us electrostatic potential. So within the solve section, we define a sequence of solutions. For example, for whatever biasing we have defined initially in the electrode section, for that initial condition, we do the initial solution. So this solution will solve for potential and charge densities for initial boundary conditions. Then we can ramp the electrode boundary conditions, for example, voltage boundary condition from, for example, drain voltage from initial to some final value. Similarly, we can ramp the gate voltage. So this is how we ramp the contact parameters within the solve section. So as I said, so your initial, whatever initial biasing defined, initial boundary condition defined in the electro section, for that we are first initially solving this initial solution for this electro section. So this is required for your generating band diagram for initial state. For example, if you have not defined any biasing in your electro section, then you can plot your energy band diagram under equilibrium condition. Then now here is just saying that this coupled equations will be solved for these many iterations to get this the solutions. So usually a higher value of iterations is initially used to get to see that the convergence happens. And then this Poisson and so in the second line, this Poisson and continuity equations are being solved self-consistently, and boundary conditions at the electrodes are taken into account. Then during biasing, so for quasi-stationary biasing, quasi-stationary in the sense as a function of bias change or potential change within the device, our electrical entities like carriers can electrons and holes for that matter, they can change they can respond to that. That means this is having so it seems like everything is happening so statically that carriers are able to follow the changes in the potential. So quasi-station in the quasi-station, so that is the this is what quasi-stationary means, and we can define how this quasi-stationary solution will means happen. So we can define initial step, min step, max step, and increment decrement for our voltage ramping. But these terms, initial step, min step, are actually defined for a internal variable t, which we'll see later, and that t is ramped from 0 to 1, and that t will be used to calculate the voltage values at different time steps. So this is our general structure of solve section. So quasi-stationary is ramping the electrode voltage to desired value, and now whatever electrode name we are using in the goal section, we should see that whatever contact type we have defined. For example, if we are ramping gate, we are ramping voltage, then we have defined voltage boundary conditions for that contact in the electrode section. So as I said, when we increment during the bias ramping, when we increment the means step sizes, so what we actually do is we are changing this t from 0 to 1, and in each step the change value of t is used along with the means previous volt along with. So this is your initial voltage. For example, in our case, it is 0 volt, and V1 is our final volt. And this t will vary from 0 to 1. So when t is 0, so we have at 0 time instance, we have 0 volts. And when t becomes 1, then we will have V, final voltage. So this t will change during the ramping. And in that way, bias at different timestamps, we will get bias at different timestamps. So usually the default value of initial step, that is t 0.01. Default value is 0.1, but to get good convergence, we should usually use a smaller value. Then max step is by default 1, but we can reduce that. Similarly, min step is 0.01. We can also change that. So we can change these parameters as per convergence issues. So to get better convergence. So by default, this increment, the time step increments by 2. If on the previous previous solution, the solution was successful, previous iteration, then time step will increase by 2. If means for example on the it is not converging, then time step will divide by 2, and again our biasing will be we will simulate at a slightly lower bias. So for example, for successful convergence, then your increment means your time step increases. For convergence failure, your time step decreases by default. The default is 2, but we can change this. So we can here pictorially it is shown how is this t variable changes. So for example, you start from t is equals to 0 now. If you have at the initial bias condition you have successful convergence, then your t will increase. Then here also you have successfully simulated, then the t will keep on increasing with this increment factor, and finally the increment, so that this step size will keep on increasing till it reaches max step, and if once it reaches max step, then it will not increase further, and consecutive means consecutive simulations will happen with max step max step time step value. But if at some point of means our ramping, if we see that there is a convergence failure, then max step will become half by default. If increment and if decrement value is 2, which is by default, then our step size will half, and then at this bias point, this simulation will try to converge, and then again it will move forward. This is how this ramping of this implicit t variable happens, and this increment, which is defining the step size, this is how the increment is. This is the formula which is used to define the increment, which finally determines your step size for each iteration, for each bias point. So as I said, if your simulation is running fine, so all your after some time all your data will be generated at a distance of this max step size. So if you define max step size too high, so for example in this case, for example, max step is high, in that case the whatever output is being generated, so you can see that this is not very smooth. This is a coarse diagram output. So you can keep max step small, so you get a very smooth curve. So numerical solver settings. So in the mass settings, you you define the whatever numerical methods or whatever control settings you want to use to for your simulations. For example, extrapolate iterations, we saw that it will take these many iterations to solve at a particular bias point. So by default it's 50. We can keep it low. For initial solution we had kept it high. So this means how the simulation will run this math. So math section is defining the method. So for example, iterations, let's see iterations. So I will give you a general example of this Newton-Raphson method. So for example, we have some function, we have some variable x, and we have some function f of x and its derivative f dash of x. So we start with some initial assumption that let this could be our initial solution. So let x not be our initial solution. Then we will calculate our next solution x1. So how? So using this formula. So in the next step, x1 will be calculated now. So and the difference of x1 minus x0 will be compared to some predefined error criteria which we have already stated, that once our whatever error xn plus 1 minus xn becomes, where I am referring n to iteration number, so becomes less than the error criteria, then we will say that at that bias point the simulation has successfully converged. So this equation will be solved iteratively until our final xn plus value, which comes very close to this x, which is our required solution for the given f of x. So for example, here a snippet is shown where it's saying that this solution converged because this RH has become less than the some predefined this predefined error criteria. So usually means for means bias ramping, we usually recommend that you keep lesser iterations, because as we can see, means usually this 6-7 iterations are enough for convergence, and if it has not converged till that point, then you can understand and it will not converge, and it's better to use redefine our min step max step values, then instead of just going into this iteration loop. And so just define a lesser value of iterations. And in the case of extrapolate, so for example, we are biasing, we are ramping our bias. So here in means, for example, here our solution variable for our x-axis, we have our solution variable nicely converge. So this extrapolation takes into account whatever the solution output from the previous ramp point. So for example, if suppose we are here while we are ramping, for example, some voltage, and we are here at this point. Now if we are using extrapolation, then for next subsequent solution, the solver will use the value this as the initial value if we have extrapolation turned on. Else, if it's not turned on, then the solver at this bias point will consider this as the initial value.
अभी भी license का issue आ रहा है इसमें.
So I will request that please
मैडम
keep yourself mute. So if so I was saying that if extrapolation is if not on, so in that case, for example, if we are at this bias point and we are trying to achieve convergence, then it is difficult to achieve convergence, since the difference between initial solution and final solution is quite large. So extrapolation will help us achieving the convergence faster. Now this .sav files which we discussed initially. So this keeps snapshots of the present bias conditions. So this when we take a snapshot, for example, we are here and we take snapshot at this bias point, and when afterwards we want to simulate the device starting from this same bias point, then this .sav file will also contain information of extrapolation if we have included it in our math section. Then what are the physical quantities which will be plotting within our _des.tdr file, and as well as in the .plt file. So plot section. The plot section in the file section, the plot file refers to the _des.tdr file, which will be generated after the successful run of SDevice tool. And once it has run successfully, the TDR file will be generated and various fields will be stored. The fields are the values which are stored at, for example, in 2D case at different XY locations within the structure. So these variables are stored in the TDR file. So solution variables like means our SDevice solver is solving this continuity equation and Poisson equation. So whatever variables are going into those equations and being solved, like carrier density, then potential, those, and for example lattice temperatures, whatever is being used to solve those equations, those variables will be by default included in the TDR file. But we can also then additionally include other variables as well. For that, we need to include those keywords within the plot section of the command file. Now, so they are Poisson, as we have said already, the Poisson equation yields electrostatic potential, and from the electrostatic potential, we can derive this electric. So electric field is the derived quantity, which is the gradient of the potential. Similarly, so this electric field we can then state additionally. So additionally we need to specify this keyword in the plot section. Then it will appear as a data field within the data selection panel of your this SVisual whenever you will open the TDR file. And solution of continuity equation will give us electron and hole concentrations, and the derived quantity from that is your electron and hole current densities. So these things we will include in the plot section, and so that we can see it in the TDR file. So specify various variables which you want to include in the output TDR file. Then, for example, here I have included additional variables like doping and electron density, hole density, or electric field. So we can specify vectors. For that, we need to specify this specifier / vector. Then that particular variable will be stored in the form of vector. Then others are stored in the form of scalar. Now, yeah, so various variable names, you can find it here within your SDOS manual. So plots, and so in the solve section, so we saw that we have defined means plot section as a separate section within the command file. Means we had file section, we had electrode section, we had physics section, then we had plot section, then we had solve section, math section, solve section. Now, in addition to that, we can also specify plot files within the solve section also. When we are, for example, when we are ramping some node the contact voltage, then within that section, solve section, we can also specify a plot command. So this plot command will take a snapshot of that and of the device structure at that particular biasing conditions, and it will store in the TDR in a TDR file. So for example, in this case here, this in the solve section itself, now it is showing. So it was ramping. So here this is the initial solution with initial boundary conditions applied to the electrodes. So in this case, it's showing that now it's plotting this N3 underscore equilibrium. So whatever suffix we have applied, we have attached to this name, then that is shown here. Now when we are ramping, then this ramping the bias, then the bias will ramp, for example, whatever VD value has been specified as a SWB parameter. So this @VD is an SWB parameter, and it is called in this fashion within the command file. So once this voltage has, this has reached this, then for example, your drain ramp has reached this value. So this will take a snapshot at this, it will save a TDR file at this location. Similarly, when your gate voltage has finished biasing, means ramping till 2.5 volt, then after that, once this goal is finished, then finally whatever plot section which you had, whatever name which you are using in the plot section, that will be, and finally this your final TDR file will be stored there. So for example, in the plot section, we had defined at the rate TDR dat. This thing will be replaced by this N3 underscore TDR des.tdr at the end of simulation. Similarly, when we are we can plot the current IV data in different files by specifying this specifier new current prefix. So for example, in the command file, we have stated that whatever current output, IV output is being generated, let's store it in this plot file, this file name. But if in our solve section, if we define that now, if, for example, if I need to store my IDVG data in some other file, then I can include this new current prefix file at that location. And from here onwards, when as the simulation progresses, whatever my IV data will be generated, it will be stored in this file. Similarly, here one more file was defined to store this, to store the this IV at during initial for initial conditions. So this is how now means once this after this step, the IV data won't be written in this file in the whatever initial file we had means defined in the file section. After this step, the data will be stored in this file, and you can define this new current prefix multiple times within your solve section. This is
Narendra,
huh.
when do you plan to give a break?
Yeah,
Because you have been going on for 1.5 hours now.
So should we take? So it's 11 now, huh?
Yeah.
So let's pause for 10-15 minutes, then
So
we'll
let's
resume
start
from.
at 11:20 now. It's 11:03. Let's start at 11:20.
Yeah. So Samir, Samir, sorry, Prince.
Yeah,
Hello.
sure, sir. We can
Yeah,
schedule.
yes. Yeah. Okay, Prince.
Okay, so let's meet at 11:20 now.
Yeah, yeah.
Yes, yes, actually, I will look for them. Check in the received it today. So I am
Hello.
And then
Hello.
you're audible
Yeah.
now.
Yeah. So Prince, can we resume?
Yeah, sir. Please proceed, sir.
Yeah. Thank you. So we we saw that we can save .plt files within the solve section. So so as I said that after this new current prefix file, for example, here onwards the current will be stored in this file. So this file now we are viewing in CentOS Visual, for example. So this file can be loaded. This file can be loaded within the CentOS Visual, and you can see IDVG characteristics. So basically here I would like to I would like to stress that basically when whatever I have explained for this IDVG underscore M3, that name should appear here, that data set. And data set name will be here. So this in general I'm showing you an IDVG characteristics, but remember for this PLT file a data set named this will be created without extension, and that data set name will appear in this data selection tab of the S Visual, and from selecting that tab we will see this means once we go into SWV. So current file and current plot sections. So so as I said initially, that means you can additional to the .plt file IV, whatever IV you are generating in the .plt file, in addition to that you can also save the values of means the values which are calculated in the structure at some either at some special location or averaged over the entire region or entire device or some material. Those informations can also be saved in a form of XY data, and can be generated in the form of XY plot, like as a function of bias. For example, in the current plot section, if you define H density and then you are performing your bias ramping, then H density at this XY location will be saved for all the bias ramps, and you can generate that as a function of bias and XY plot. Similarly, for E density, if you are taking average over the semiconductor, then that average a single value average value will for different biases will generate an XY plot. Similarly for other entities. So this is also possible in addition to the IV plot, which is also called XY plot, which we generate using our current file in the file section. So this is, for example, this is an example where in the current plot you have defined some entities or some variables which you need to plot after this bias ramping. So you can see that in addition to whatever these options which we have available for plotting IV, in addition to that we have one more option here now. Integrate. So this is the keyword which is being used, integrate semiconductor. So now when we can now plot as a function of drain or as a function of gate these quantities which are stored here, and those were stored by using this current plot section. So plot command, we already saw that inside quasi-stationary or transient, I would say transient ramping of the bias. So the plot section was, the plot command was used within the quasi-stationary. For example, we wanted to save the snapshot of the TDR file at some bias. So initially we did not mention the actual value of the bias. So it plotted after the goal was done. Now we are here explicitly in this example, we are explicitly saying that plot a TDR file when contact node or node voltage becomes 0.9. So during this bias ramping till 1.1 when it's at 0.9, so the at node voltage is at 0.9, and then at that time our .tdr file is being saved here. So this is also an option available to you at what bias point you want to save a TDR file to look into the various data fields within the structure. Now, one more option is there that you can save your snapshots of the TDR file at regular intervals. For example, if you, in this case, if you specify intervals is equals to 10 over the range 0 to 1. 0 to 1, this is your implicit t variable going from 0 to 1. That is you are ramping from some initial node voltage to final node voltage. So during that entire bias ramping, you will store 11 snapshots at the intervals of 10. Means 10 intervals, 11 snapshots. So at 0% of completion of bias ramping and going up to 100% completion of your goal. Now solve section. So we have seen this quasi-stationary ramping. We have been discussing this. So we have been discussing means basically the voltage ramping at an electrode. But in addition to voltage ramping, we can also ramp a parameter in the solve section. And then we can save the this .plt files at some fixed values of ramp or bias. So this again, you see this current plot is different from this current plot section we have been discussing. Means we had discussed initially that in the current plot section we can define some entities which will be plotted at some xy location and can be visualized as an xy plot in the .plt file. Now, in addition, this again we have a different current plot syntax here, which will allow us to save the current versus voltage data at some predefined voltage values. We will see that. Then plot statement we saw. Then we also saw save and load. So I already discussed that save will save a snapshot.sav file, which can be again called back to resume our simulations from there. So calling back will be done using load. Then in addition to quasi-stationary, we can also ramp the bias as a function of time, you will see. So this we have been discussing quasi-stationary. Now we had discussed our goal. Initially we were discussing that our goal was some contact contact name. Name is equals to drain something, and then voltage is equals to something. Now instead of that, we can also ramp parameters, material parameters. Like here, trap energy is being ramped up to some max ET value. So this ramping is in the similar fashion as we ramp the contact voltage. So what parameters can we ramp in this fashion? So the name of those parameters can be obtained by if you just run this command on your command prompt. Wherever your command file is located, then you will see a list of parameters which can be ramped in this manner. Now output file what is current plot. So now this current plot, we are now plotting this IV data at some predefined voltage values. So in this syntax, this will store the values of I as a function of V in n number of intervals or n plus 1 number of voltage positions. So by doing this way, we are forcing the terminal current to be written in n intervals, because when this SDY solver runs, so it might face some convergence issues. So it might solve the solve the equations at some intermediate values also. So there are IV values are generated at different values of voltages, but if you want to plot or data only for some fixed values of voltages, then you can then explicitly state like this, that I only want this 11 data, 12 data, whatever in the PLT file. Now the plot section, we saw that file prefix, and when we write like this, then we are storing a snapshot of a TDR file. So we can also store it at some predefined for example, voltage values. So this again, this time is our implicit t variable. So when, and it goes from 0 to 1. So when that variable is 0.1, then take a snapshot. Then at 0.3 and 0.8. So 3 snapshots in this case. If we say that no, take snapshots over the entire range at in the intervals of tens, and then again these 11 snapshots will be saved. These are your TDR files, file prefix. This generates your TDR files at these bias stages. Now again we saw means .sav file. We can save a snapshot of the device at some bias, and we also said that the extrapolation that extrapolation value will also be saved in that .sav. And when we again call that .sav file using this load syntax, then we can resume our simulation from there where we have saved that file. So that .sav file contains your restart information, including in your extrapolation information, and wherever it is called, then your Cauchy stationary ramping starts from there, commences from there. And extrapolation will be applicable will be used wherever it is applicable. Then the TDR file snapshots which we saw means plot by using this one, file prefix. These also can be used to commence a simulation from a previously stored snapshot. But yeah, so that can also be that TDR file can also be used to commence our or resume our simulations. But usually it usually stores a lot of data and consumes a lot of memory, and usually then that this thing or reloadability can be switched off by using this no plot label syntax, plot loadable syntax. So this is again regarding the ramping only, not particularly related to transient simulations, which will be cover later. So we have seen that in the solve section we were ramping the, for example, contact voltage by using quasi-stationary ramping, but we can also do a transient ramping. But in this case, that this initial time, final time, initial step are in terms of seconds, actual timestamps. In previous quasi-stationary ramping, it was that implicit t variable. Its value was being controlled by these keywords. Now actual values of time will be controlled by these keywords, and it is in seconds. Now, for example, means we saw that instead of giving a fixed boundary condition in the electrode section, we can give a time-dependent boundary condition in the electrode section. For example, let's see an example that if in the electrode section we get for gate contact we define voltage like this. So and we run a transient simulation so it is creating a piecewise linear graph for voltage as a function of time. So for example, at 0 seconds it's 0 volt, then at 1 second it's 1 microseconds it's 1 volt, then it remains at 1 volt for 12 microseconds. This is how the voltage at the gate contact is propagating as a function of time if we specify the time dependent bias time dependent this boundary condition for voltage this gate contact. So this is how so just means in the quasi-stationary we were ramping it linearly, so we can also control the shape of the ramp in this transient case. Now turning points. So again this time step the value of time step changes in this transient means ramping as well, means your simulations are converging correctly, then your time step will keep on incrementing with this as a factor of this. So for example in this case itself, so in this flat section the voltage remains at constant over this time range, so the convergence will be very good. So it will your time step will increase fast. And suppose if you are somewhere here, then time step has already increased a lot. And for the next time stamp, you are here, you are simulating here. So suddenly there is a lot of change in the bias. So your simulation might not converge. So in that case, we can specify the turning points. Means the turning points, we can particularly specify the timestamps where we want to use a lower value of this time steps, so that our convergence happens, that our simulation converges. So we can explicitly define time means time steps at these turning points. This is what turning point is saying, that it helps us to force solutions at given times, and then we can continue with specified time step. So it is usually helpful in breakdown voltage simulations because, for example, if you are simulating the breakdown characteristics of a diode, suppose, then for over a stretch of reverse biases, the current remains very slow, very low and flat, and suddenly it starts becoming vertical. So in that, wherever it's becoming that changing its shape in that voltage range, you can just reduce your time step and then obtain convergence. So here means till now means I have discussed means how we can ramp the means, for example, contact voltage using quasi-stationary, and also here I also explained you transient. Now let's try to see means or run our examples and see what is there within the project file which was shared with you. So let me open my SWB. I hope you people are able to open your SWB and extract this. Initially, Sushant also showed that directly means day after means yesterday, day before yesterday, I had shown you means how you can first reach here your DB directory, and then from here you can just open a terminal window and then you can copy paste. But in yesterday, Sushant showed you that while launching the SW itself, you can run with this SWB, this file name, and then you will be here. So I hope you can open this terminal. You can open this window, your project, since you were able to access your project here. Means initially you were working here with this process. So now uh, we are moving forward with our SDWise tool. So let's I have already shown you a structure for this. It's command file. Let me open it again. So this is the command file for our IDVG lin. So IDVG lin means basically means we are first setting the drain voltage at a very low value, and then we will ramp the gate voltage. These all different sections of the command file I have already explained. The file section. This is your input file. So the input, the structure generator from the CentOS process will be called here. Then this is your output. These are your output files, and node specific. In our case, yeah. So node specific output files will be these names will be replaced by node specific file names. This is your electrode section. So we have discussed these different file sections within the command file. So this is the quasi-stationary ramp. I am ramping in this first quasi-stationary ramp. I will first ramp the drain voltage up to VD lin. So once my device is biased at this biasing point, then I will ramp the gate voltage up to VDD and to generate the IDVG. So up till this point, the IV will be stored here in the current plot file which we have defined here. But now after this point, I am deciding, no, I will now save my IDVG in this file. So it will be stored here, IDVG. So let's plot this. So means on the first day of the session, we had discussed what are the different ways in which we can simulate the data. So means if we have already defined a SVisual tool to plot the data, so we can use this run visualizer, this visualizer select visualizer node, then we can directly run from here. So I'm directly running from here. So see, this is generating me voltage, gate voltage versus drain current plot. So this is the IV which is being generated, and at VD is equal to 0.05 volts. Now I want to again, if you remember, on that day, means I was doing, means I was trying to open this IDVG. So I did quickly visualize. So sorry. So this is the S visual tool. So since it does not have the file specific to this quick visualize, that's why it gave me an error. So now here I have simulated this as device tool. If I select this node, now I quick visualize, so it will open the .plt as well as .tdr files, whatever visualization files are there. So it will open this. So if you remember, on that day I was doing one mistake. Means I was manually trying to plot this IDVG, and I had selected this file, and when I was doing this gate voltage to XX, for example, inner voltage, and drain to total current, and when I, so just a minute. So this is my data stage, the gate, inner voltage to x-axis, and drain total current to y-axis. So it was giving me this, and I was confused what is happening. So it's only because, see, this N10 underscore DES. Sorry. So my node is N10, and I said, as I said, this in the file section, my IV current is being generated in. So this plot will be this name, reference name will be replaced by N10, since I am referring to N10. So this current was the IV data will be stored in N10 only till this point, and after that point, I had defined this IDVG, and so on that day I was trying to open this IDVG. So it was not showing me any curve because I was choosing the wrong data set. Now this is where my subsequent solution variables were stored, IV were stored, and I should have chosen this thing. So this was the mistake I was doing, and I wanted to point it out this time. So IDVG lin we saw. Let's also quickly look at the IDVG sat. So the shape is IDVG is similar shape of larger value compared to Vigilin. Let's compare them simultaneously to see the effect of VD. So let's select both the nodes together and run with the visualizer node. So see, so for lower value of drain voltage, I'm getting lesser current, and for larger value of drain voltage, current is higher. So this is how you can compare IV generated at different nodes simultaneously using our within SVisual. So and IDVG sat. So for IDVG sat, you means you will use you will use a larger value of VD voltage. Now let's again let's now see this command file of IDVD. Okay, so rest of the things up to math section remains same. In the solve section now, see, so first I am doing a quasi-stationary ramp on gate voltage, and I am ramping it to VG1. And see, I am using this save command to save a .sav file. So something n node number underscore vg1.sav will be saved. Then again, I am doing a second VG ramp, and I'm storing it up to, I'm ramping up to VG2, and I'm storing it into a second file. Then I will, then in the next quasi-stationary ramping, I will, so first of all, I will use a different now plot file. I will define a different plot file where I want to save these IDVD curves. Now I'm loading this, whatever I saved. So I will load that .sav file. I'm loading this, and now I'm performing IDVD simulation on that. Similarly, I'm loading the second .sav file, and I'm performing IDVD. So now I will have IDVD at two different VG voltages, VGs. So let's also look the current which was generated there. So let's visualize this IDVD. So see, so one IDVD I have generated at VG is equal to 0.5 volt, and another IDVD I have generated at VG is equal to 1.5 volt. So at this point we are pretty much done with this DC transfer, which is IDVG and output IDVD curves. I would encourage you. I will give maybe 5 minutes or 10 minutes to plot an IDVG lin, simulate an IDVG lin for a VD lin of 0.1 volt. So what I'm asking you is that add a parameter, VD lin parameter, in addition to 0.05, add a parameter to 0.1 of 0.1, which will create another experiment for you. You will see another horizontal line, and then run the simulation, run your SDVice tool, and generate the IDVG lin curve. So can you try that? So if you remember on the first day, I had discussed how we can add parameters. So if this is this VD-lin is one parameter, so you can add one more value to this parameter, so it will create another experiment. So first, instead of telling you the answer right now, I will pause for 2 minutes and let you guess that how you can add another value to this parameter so that another experiment is created. Please, whoever has opened this SWB window and able to access this project and can see this experiment, please try to add one more VD-lin value, one more value to this VD-lin parameter, and try to generate IDVG-lin. And try to generate plot IDVG underscore lin for that value. I will wait for 2 minutes, then I will show here. But I want you to try, at least think. Okay, so yeah, if you Akash, if you have added, then please run it and generate your plot IDVG. So on that day, I also showed you how you can choose the nodes separately. Instead of running whole simulation from left to right, you can select particular nodes and also run. So just try it out. I will wait for 1 more minute, then I will show it here. So let me show it here. So VD-lin, this is one parameter I have defined. So I'm right clicking on it, and then I will go to add parameter values. So I will just add one more parameter here, 0.1, and then add it. So here you see that for my VD-lin parameter, another value has been added and a second experiment is added to this, our experiment tree. So now we can specifically choose these nodes which we want to simulate. For example, this and this. Since this tool has no dependency on this, so it should run fine. So it's running. See, if you notice how the node colors change from white to green to blue, then finally in the run state, it becomes yellow when simulation has completed. So it's showing me done. So now if I plot this for 0.1 volt, so let me use quick visualizer. So it has produced some IDVG. So we can means appreciate the change in value of EDLIN by comparing it with the previous value. So let me select both the nodes and run the visualizer node. So you can see for VD is equals 0.1 volt, the current has slightly increased. So means the simulation is working fine as we expect. Means for a slightly larger value of drain voltage, we expect a slightly larger value of current as a function of gate voltage. So this is how we can add parameters. Means we can add value to the defined parameters. So I did it for ID Vigilin. You can afterwards practice it for yourself. Or these are all various parameters, VG1, VG2. You can play with those and you can generate different curves. So at this point so our transfer and output characteristic discussion is done. So let's move forward with our presentation.
Narendra, can you hear me?
Yes, Sushan.
I mean, there have been some questions like on Ganham and I don't know, like polysilicon as material to gate, some Hemd area factor. Maybe you can comment on those. Just wondering. Or you can comment later on also. But
Yeah, we can take it later.
Yeah, sure.
Yeah. So let's resume with our presentation. So turning points we had discussed. Now, yeah. So there is this tool, CentOS Device Wizard. So it allows us to create ready-made projects and to perform this edge device simulation and get IV characteristics. And there are there are number of examples provided within this edge device wizard facility, depending upon various application areas which you can explore. So let's just quickly discuss this edge device wizard. So from where can you access this? So let me again go into this. So this is my SW window. Again going to trainings. Then in the trainings, so if you see edge device, so here edge device. Oh, sorry, just a minute. So once you go into your training, so it's in CentOS Workbench. So let me again start from here. So so let's go to trainings in CentOS Workbench. Here you have your CentOS wizard. So here, I mean, you can is a a short tutorial on how to use CentOS Wizard to generate ready-made your projects and perform your device simulations and get electrical and observe electrical characteristics. So this is where you will find the tutorial. Now let me just. So once you click on this is the document tutorial I was showing you. Yeah. So let's quickly do a hands-on how we can do this in SWB. So for that, let me first create a blank project. So this is your blank project, and you can see that it is temporarily being stored in the temp directory. Now we'll first. So let me first run you through the whatever lines things. So this is how is your flow. So we'll first add a SDevice tool to in the tool flow. Then in that we'll go into edit input and we will edit the SDevice. So we'll see here an SDevice wizard option. When we click on that, then we will go through these sequences. Then means we'll first choose an application area. Then we will then select a device. And then we will choose what simulation task we need to do on that. Then depending upon the device we have chosen on simulation task, then we will define the appropriate physical models. We will choose the appropriate physical models. And then we will customize our numerical settings over there. Then we will, when we click on finish, then it will create a project for us. So let's do that. You people can also do it simultaneously as I am doing. So here we have, here is showing no tools. Then first we'll add a tool here. So right click, go to add, go to tools and add an SDevice tool there, keeping the default settings. Click OK. So this is an SDevice tool. Now presently it does not have any command file. So now let's right click, then go to edit and go to SDevice wizard. So see this menu pops up. So now, so application. So what application basically we want to choose? So so these are various. So you can choose any of the applications and you can continue forward and it will generate a ready-made project for you. So after you after these sessions, you can again revisit this and look for application specific areas of your interest, and you can create a ready-made projects and just go through them. So let's select a two-terminal device. Then so we have opted for a two-terminal device. In that, let's opt for a two-terminal capacitor. So it's 1D MOS capacitor. Please, you also try it, and it's just clicking only. You just need to click. So choose a task for simulation for the selected device and then press OK. So let's, I am choosing to simulate this low frequency CV with various quantum correction models. So now I am, once I have chosen the device and what simulation I want to do, for example, low frequency CV, then specific to that, I will include various models. I will not include this MLDL model for timing. Let's just stick with this general one. Then click next. Then we will use a solution extrapolation, which we discussed. Then customize numerical settings for selected device and click next to proceed. So now we will we also want an SVisual tool to visualize our results. So yes, we will keep it. Generate SVisual tool for post visualization. and this will be the label of the tool, SVisual tool. And so here we are, since we are directly starting with the S-Device tool, so we do not have a predefined TDR file which we had initially, which was generated from S-Process. So we will use whatever TDR file this environment is providing, this SW Wizard is providing to us. We'll use that TDR file for this 1D MOS capacitor. Then next, so this gives an overview of whatever you have chosen for this particular simulation. Then let's, so someone is saying this wizard tool is not there for us. I don't know about that. It should be there. So I cannot comment on that. So let's finish this. So see, after we are done with defining a project through S-Device wizard, we will see a tool flow like this in our. So this is S-Device tool SVisual. I hope at least some people would have managed to generate these two tools. Now, so let me save this. So let me project, save as, save project. So it will give me an option where to save the project. So let me save then DB. I have already let me save it with the name SDW Center, the device wizard MOSCAP 1. So okay. So once this project is created, see, so I have already saved one project SW. So I have saved another project. Now select that project and then run it. Okay. So let's see. Commands. So you should. So once you have, I think somebody's question was, so once you have added this S-Device tool, when there was no tool, then you added S-Device tool, and when you right click on that, and you went. So when you right click on that, when you edit it, so you go into S-Device wizard. From there, that window will pop up for you. This window. Go to the S-Device wizard. So see this. The simulation is run. Let's just quickly see what output it has generated. So this is the low frequency CV. Since I had chosen to simulate low frequency CV for this 1D MOS capacitor, so it has generated low CV. So if you can recall from your MOS capacitor theory, so please verify by yourself that does it resemble the curve, low frequency curve, which you usually see in your textbooks or 1D MOS capacitor. So this is basically we have, yeah, so this is low frequency CV. So I hope at least some of you were able to generate this curve from the S-Device wizard. So this is regarding S-Device wizard. Let me now continue with this presentation. Yeah. So we performed these steps and we then generated we created a project for 1D MOS capacitor and we produced LFCV. So actually I also wanted to ask you to repeat the same steps for generating HFCV. If you had seen this, means when we had chosen a task to be simulated for selected device, then there were two options. One was LFCV and one was HFCV. So I chose to simulate LFCV. I wanted you to also simulate HFCV and see the difference between HFCV and LFCV. But right means I feel that I should you can do that later for your practice. I should move forward with the presentation. So now we are done with the DC part, transfer and output characteristics, where we generated the outputs from our project and also using SGWise wizard. Now we'll look into the AC simulations, and we'll be particularly discussing small signal AC simulation. Okay. And in transient simulation, we will see an NMOS inverter and then a CMOS inverter using a compact models. So single device simulations. So usually this AC simulations are usually done in mixed mode environment using mixed mode simulations. But for single device simulation in SDevice provides us with an option to also means use an implicit AC system, and we do not have to define a circuit for means we do not have to use mixed mode. We'll see this. So in the mixed mode simulations, we can use our physical devices. We can also use compact models for various basic devices like resistors, capacitors, and also different diodes, MOSFETs. So for the physical device, so this file section, electrode section, physics sections, they define your a device, and there could be many devices within the circuit. So these file sections we need to define individually for different all the devices. Solve section can be and then this is a common to all the devices, physical devices. In mixed mode simulation, so suppose we define, so this is an identifier for NMOS. We define a device named NMOS and with some file and electrode and physics sections. Then similarly, we can define some PMOS device. This is just an example showing how you can define your physical devices which you are simulating within SDevice, and how then they will be eventually called within the netlist, circuit netlist, to perform mixed mode simulations. Then within the system section, this V source P set is this parameter set. So this is a model actually. Voltage source model which is being connected with within the netlist. So in addition to that, we are also including our physical device which we are simulated from SDevice, and this and we are means correspondingly attaching the contacts, our contacts with the node, with the circuit nodes in this line. We are also using means built-in model for capacitor with capacitor in this. So this is just a general example how this simulation setup for mixed mode is done. So let me first discuss this small signal AC analysis. So this small signal AC analysis basically means this: once we have biased our device at some DC value, then over that we can superimpose a small signal voltage perturbation which is shown by this delta EV and delta V, and corresponding to that there will be perturbations in the current, and the perturbations, the relationship between the current perturbations and voltage perturbations is defined by this admittance matrix, which is nothing but the sum of your conductance matrix and this capacitance matrix, J omega susceptance matrix. So now, so as we saw, we are means whatever contacts we had defined for our device, then we connect it to the terminals within the netlist. So let me just, yeah. So for implicit AC. So now, for example, we want to simulate small signal AC, AC for a device which we are simulating in CentOS device. So for that, if we are simulating AC implicitly means we just have to include this implicit AC system within the math section and an AC coupled section for performing the AC simulation within the solve section. So this AC compute is optional. It is just saying that we are just storing 41 voltage IV points, but these two syntax or keywords are mandatory. This is also mandatory where you want to save your AC plot. So having defined these three keywords, then S device allows us to perform implicit AC even without defining a system or netlist for the simulation. So this is just a snippet of the command file which looks like this for implicit AC. I'm just showing you here this file section and this solve section. So this is a general explanation. This in the file section, you are specifying a file name where you want to save the data that is being generated from AC simulation. This is just the equation for your admittance, conductance plus j omega capacitance. These are matrices. So depending upon number of contacts, these are, for example, for n number of contacts, this is n by n. A and C are n by n matrices. So this is how your system section is being defined, where you are just attaching your contact definition electrodes to the circuit nodes, and here you are defining some built-in voltage sources you are using and giving it. You are initializing with a DC 0 DC value. Then when you perform the quasi-stationary ramp, so for transfer and output characteristics, we were doing coupled. In the goal, after the goal section, we were doing coupled, and then we were doing these things. Means we are using this increment, decrement, initial step, and then we were doing those things. But in the AC coupled case, we are defining the frequency at which we need to do the AC simulation and which nodes should be included during the AC simulation. And we are excluding the DC voltages at those nodes because anyways, the DC acts as a short circuit for AC simulations. And to get correct AC results, we are just excluding those DC voltage sources from the AC simulation. So this is the structure. So this is the input file I'm showing you for. So I have already showed you implicit AC where we needed to just incorporate these three keywords. Rest all the syntaxing was similar, at least till math section, as similar to the DC thing. Only in the solve section we needed to include this AC coupled thing. But now in mixed mode case, you need to define a system here. So we are defining a file ACStat where we want to save this simulation data. But in mixed mode, in addition, we are defining this system section where we are defining the connections, various connections within the between the nodes. And here again, so this is again your solve section for this AC simulation. So this extra system section is being defined here. Now, so these are the results which I have plotted from our this project. Let me just quickly show it from there. So again, let's go to this project which is shared with you. So I have already simulated this. I have shown you the structure of command files for CV implicit. This device S device command file and This I have shown you. So directly let's visualize the results. CV results. So quick this run visualizer node. So now this, so actually this has overlapped. So actually, so this is the initial project which I showed you, but basically the figure I'm showing you, I had later means made changes in this S visual syntaxes to just, for example, let me just open it. Just a minute to show you the S visualizer. So this, okay. So this is the graph which I'm showing you in the presentation. So basically I have just made a little bit changes in the plotting of this curves in the S visual .tcl file. So that's that. Now let's again go to our presentation. So this is what I showed to you. And within this only, so just a minute. So if we look closely, so this node number 24 corresponds to this implicit, okay? Implicit curve and data set, and this node number 27 is for mixed mode. So if you see this naming scheme, so for this implicit thing, this your naming of this, for example, capacitance between source and drain. So its naming is like that, n underscore score and then n underscore drain. Whereas for that mixed mode part, so it's using this node this labels. So this capacitance between drain D comma D. So D is our drain terminal. So this is the naming difference. How the values, means capacitance and admittance values will be stored if you generate it using implicit and mixed mode CV. So this is the difference I have shown you here. So now let's, so we are fine, Prince, we are fine, we can continue now. So anyway, it's nearing only. Hello, am I audible? Okay, so let's continue with this NMOS inverter. So now, yeah, okay, fine. So after completing this small signal AC, now we'll see this inverter, NMOS inverter characteristics. For this, we will need transient simulations. We'll see that. So, so I'm just showing you here this math section and system section. And then, so so somebody is asking how I'm getting positive values. So I am in the S visual this .tcl file which I'm using to plot that. I'm plotting the absolute values of those. You might see some negative values also of capacitances, but I showed you the means outputs from here. So, for example, if I open this, so what I am plotting is absolute values of those things.
here. So I'm taking absolute, if you can see absolute of, so that so whatever graphs I have showed you, those are only showing positive values. That's why. Now in inverter, so I'm showing you the system section. So here, and this we saw that how a voltage source is being generated and a DC and initialized with a DC voltage value. Here now I am using a pulse. I am defining a pulse voltage source, and this is the definition as a function of time. Then again, this is our device which we from our edge device edge device related this physical device which we have taken from this CMOS sorry, CMOS not S process TDR file. Now this this capacitor and resistors are some built-in models for capacitances. So this forms your system thing system, and then this I'm also including this where to means what things to plot here in the system itself. So it will plot time, then node voltages, and then at input and output, and then currents through the elements, for example through the transistor or through the resistor at means at that particular node. For example, I NMOS out, so that current through NMOS but through this out, so the current like this. In the solve section, so this is your couple iteration. This is the Poisson. So here, in addition to our Poisson electron hole, we are also solving for contacts and circuits. And in quasi-stationary, then again when you will ramp your input voltage. So first you are ramping your DC. You have initialized with PD and this drain voltage with 0 volt, but you are ramping here up to 2 volt. And now I'm specifically, since I'm using only NMOS, I'm specifically using this was NMOS dot Poisson. So this Poisson and this electron and hole continuity equations and those will be solved, and contact equations will be solved for this NMOS transistor. This so and these are the various equations which will be solved in the coupled section. In the new current, so this remains as your base current name, and in transient here, so I am defining initial time, final time, and then a initial step which will increment with this value, and then I'm defining a maximum state, a minimum state. But here also, again, in addition to that, I am defining turning points. I already discussed with you what are the turning points, because you can see this, my V in definition as a function of time is making some sharp turning points at these time locations. So in order to get convergence or successful simulations at these turning points, I will specifically initialize simulations at those time instances, and I will define that use a very low value of time step in those areas so that simulation runs properly. So this is being declared within this sentence. Now in the next sentence, so we are defining a range of time values where a time step value will be this 1e minus 12 will be. So this range is nothing but your this one. These ranges where again voltage is ramping very fast. So in those ranges, for example, here, then here. So in those time regions as well, we should use a lower value of time step to get convergence. So this system definition corresponds to this this circuit which I am showing you pictorially. Now NMOS inverter. So when we run that, so this is the V in versus V out curve which you will get after you have run that. So you can just check in the project which has been shared with you. If you just go to your NMOS inverter part and just quickly visualize it. So you will see this kind of, yeah, this kind of graph. This is NMOS inverter. Now, so here we used a transistor which we had and developed using S process, and we called it CDR file within the device section. Means we defined a device name. For example, here we defined a device name NMOS, and this NMOS is nothing but the TDR file which we had generated using S process. So we in the NMOS inverter, we have used a transistor which we had generated using S process, but we can also use some built-in transistors are also available. The Centros tool has interface to those. Those can be used within our simulations. For example, some spice models, prime spice models, some other built-in models within the Centros environments, and also as user-defined models. Various models can be included within the system section to run your mixed mode simulations. So for example, consider this. So there is a hierarchy. For example, this I am using this parameter set for a resistor. I'm using this parameter set and using an instance for its R1. So this is how you are calling some predefined model and using it in your netlist. So you are actually creating an instance. For example, an instance for a resistor is being created using this parameter set register, and this parameter set is being called from some device, a register device, which will have some default parameter. So here we are getting a chance to, within this parameter set, as you can see it here. So you can change the values of those parameters within the parameter set. So you are just using a device register and you are generating a parameter set from it. Within the parameter set, you can change the value of the parameters which are already by default defined for this register, like resistance, temperature, register length, width. So like this. So this is how for example, you are defining a register parameter set based upon a device register, and you are changing its parameter values. These are by default defined. These keywords are defined for this for device register, but you can change those values using parameter set. Now, once you have defined that means those parameters, then you can save it in .scf file, and you can save it in some location, for example, in your present working directory itself. And while doing your mixed mode simulations, you can, in the file section, you can call that file. This is actually path for that file. For example, in my present working directory, I have some a folder named models, and in that models folder, I have this .scf file. Then I'm just including the path for the models folder, and this solver will be able to locate that this thing depending upon the parameter set I'm using. So this is the examples which we have seen, we have produced or defined the device instance or in the system section, but it is also possible to define a device instance within the .scf file itself. Then we don't have to then define an instance within the system section. For example, what I'm saying is this. Instead of doing this instantiation here, an instance can be created within the .scf file as well. Now, so this the description of generating .scf file and how to include with this using the this in the file section by using this file path. So in this similar fashion, you can define a MOSFET as well. So I'm directly, instead of showing you an example for resistor, I'm directly showing you an example for a MOSFET. So that MOSFET, so the SCF files related to that MOSFET are stored within here in the models folder in my present working directory. So from there, these parameter sets for the transistors will be called, and an instance will be created. This is an instance name, and that will be used in our circuit for the mixed mode simulation. Now this pulse voltage source definition is similar to what we used for this resistor NMOS. NMOS inverter with a resistor. Now when we now again the simulation is similar to what we had done for NMOS inverter, but in so here when you solve this, so you will see something like this. So this I have not shared with you. I'm just additionally showing you for the sake of completion that the mixed mode simulations, in our case, we did by using a device which we had developed, which we had generated in S process. But in this case, I'm just showing you that even by using some built-in models, Vice models, we can generate, we can do mixed mode simulations. This here I'm just showing you a snippet where this parameter set is being generated for this BSIM3 device, and the parameter set name is which is given this, which I am using in the system section to create an instance of this device. These are some references for mixed mode. So if you want to explore further on mixed mode, so you can visit, you can explore this here. So for example, let me just show you one within get started as device inverter compact model. So we have under applications library, we have getting started, and under that we have as device, and in that for example, inverter compact model. So this is from where I was showing you the results. So these are whatever project folders are stored within our applications library. These are only read-only projects. You need to first copy paste these projects in under your DB directly. Then only you have the right permission to that. Then you can simulate. So I'm just showing you some extra resources where you can just go to and just look for this mixed mode simulation. So these are various projects which you can access in through our SWB interface. Further, you can also go to this link and see more details on compact models. So these are all the things which I needed to cover in this session related to this DC, IV, and transfer and output characteristics, and in AC section, small signal AC, and in transient I showed you inverter. So mixed mode simulation of inverters for single transistor and CMOS inverter using compact models. So I am done with the presentation part.
Thank you, sir. Thank you so much for the presentation. So now the session is open for queries. So participants can unmute themselves and they can ask the questions. So one by one, we can take the questions, or else you can type it in the chat box. You can have one question. So there is one question. Can you please show me again how to open Wizard?
Hello, how to open? Can you please repeat how to open what?
Yeah, how to open the Wizard in SWB CentOS, because in my system it is not showing. There is a question from Lakshmana.
So see, let me first share my screen. So my screen is not shared, no?
No, not shared, sir.
So Now, is it showing now?
Yes, sir. It is showing.
So, edge device wizard. So you just first create a blank project. I think that you can do. So you just create a blank project, add an edge device tool. Once you add that, means let me quickly show it to you. So for example, I was doing this. So suppose I have a blank project, nothing is there. So here you will show it will show no tools. Then you go to add. Then you go to tools. Then in that you just add edge device tool, click OK. For example, if I click OK there, it will add one more tool. So like this, it will. So here now this tool does not have any input files. Now you right click on that, go to input and go to wizard edge device file. And from here you just need to select whatever device you want to simulate and just go on pressing next till finish. Then you will be able to see this kind of tool flow. Okay.
Sir, there is another question that how about HEMT? HEMT is asking.
Regarding HEMT what?
Yeah.
I think he's asking about the physical models.
Physical
What are the
Madhav,
models.
can you? Yes, Madhav, can you unmute yourself and you can directly ask? Madhav. In the meantime, we can take another question. Sir, there is one question from Suman. For different electrical plots, we need that many S devices tool and that many S visual in the tools flow. Sir, like sir, I saw ID versus VG and ID versus VD, two different S devices and S visual tool in the tools flow. Suman, are you there? If you can unmute yourself, you can directly interact and then elaborate your question. Yeah.
Sir, this is Madhav. Can I ask?
Yeah, please go ahead.
Sir, I'm doing on HEMT, sir. So I'm getting in a lot of physics issues. Means the physics, what are the I am applying. It has to be in the globally or region wise. So in the region wise, in the channel area, I have to apply.
So it's Algen-GAN HEMT structure you are saying.
Yes, sir.
So what I would recommend you that use first take some already application examples we have on HEMT in our applications library. So when you will
Yes,
open those files, then you will see that there is a lot of difference in model specification or this math specification of these files compared to the silicon based devices,
Yes, sir.
because this gallium nitride is a wide bandgap semiconductor and intrinsic density is very low. So you might need and also so you might need very large precision as well in these cases, since you are dealing with very low densities for some cases. So I would basically recommend you that instead of just building from yourself and trying to incorporate models, you start with an application example where there are many examples, GAN based examples, and then from those you can then use those settings, use those settings for physical models and math settings in your structure, and then I think your problem will start it means your many of your problems will go away.
Means
Conversions
the same thing I have copied and I have done, sir.
okay.
So when we are executing in the example, it is coming. When we are doing in means I have taken a traditional new one. If I'm doing means it is not coming.
Yeah, so it's not converging, you are saying. Can I know what specifically you are simulating? Means what do you want to simulate?
Simply I'm doing a
Maybe,
DC characteristics, sir.
So yeah, Samir.
yeah, maybe you can create a case. Do you have access to case Solnet Plus?
I think so. Our college has, sir.
That way we can better support you, right? Because without knowing the details, we won't be able to help much. That's the reason I'm asking you to create a case. So if you send us a project, we can have a look at it through, but that can be done only through the case.
Okay, means what are the models are given? It is given only for the physics. Means regarding to the silicon in the example sections. But the physics what we need is for an algan no GAN no, sir.
Yeah. So Naren, can you show him the getting started? There is a section on Algan devices. I don't know whether you had a look at that.
So
if you go to getting started S device module.
Okay. So let me share my screen.
Yeah.
So.
And you go to the tutorial.
Yeah. So my screen is visible.
Yeah, we can see your screen.
So I am under. Getting started S device. So.
No. Go to the tutorial, Naren.
This one, training you're saying?
Yes.
Yeah.
So now if you go to Centaurus device. And then section 16, right?
16 section is explaining about an.
Yeah.
Go to section 6. So are you familiar with this section?
Yes, sir.
Okay. Yeah. So you need to create a case that will be better. Otherwise, it will be difficult for us to help you out.
A lot of conjecture is coming, sir. It is saying that to reduce the step size. I went to 10 to the power of minus 20 also. Even though
no, that won't work. That is not going to help you, basically. I don't know. I mean, have you measured it appropriately and all, right? So all that we'll have to take a look at that, basically.
Yeah, only after looking into your command file, then we will.
And then, of course, yeah, mesh has to be appropriate, right? And yeah, there are so many things we need to look at. But did you try modifying the mesh?
Yes, sir. Means what are the values that I have? What are the examples what we are given in the SWP? The same things have been replicated.
Okay.
With the same values.
So, so tell me, so is this particularly related to this quasi-stationary you are saying? You are doing some quasi-stationary ramp?
Yes, sir.
Then one suggestion I would give you that just use a transient instead of quasi-stationary.
Yeah.
And change your time step to 0 to 1 or 0 to 10 seconds. Because as I said, means in this YDM bandgap semiconductors like ALGAN and GAN. So this, the time constants could be very large. So means, and this quasi-stationary means we'll try to try to obtain the values for that bias. Instead of that, you just ramp with the as a function of time. I think that will help you in conversions. So instead of quasi-stationary, you use transient.
Okay. Can I know the difference between the quasi-stationary and this transient, sir?
So I would not be able to give you a very detailed thing, but since, as I said, quasi-stationary means the system assumes that, for example, you are changing your bias from one value to the other. Then it assumes that whatever your carriers are there, they are able to follow that. Okay. Means, and if there are some traps or something like that, from where means where the time constant of carriers can come into picture. So then it will wait. Means I think that so that solution it will not produce the solution. In transient case, it just goes on as a function of time. It goes on ramping the voltage. And as I said, I cannot give a detailed thing, but I hope that this will help you with your convergence issue.
Okay, a small doubt, sir.
So, yeah, so I mean, I can just add something. So there's a GAN folder in power folder. Is a GAN folder. I hope you are familiar with that.
Yes, sir.
So definitely one of the examples will have a transient simulation.
Yeah.
And in transient, basically, let us say you are applying a voltage, right? Let us say a capacitor is there, right? You're charging it. So during charging, the charge is going to vary, right? That's called a transient simulation.
Yeah.
But then once it's completely charged and so that is like steady state, right? There is no time variation with time.
Yes, sir.
So that's the basic difference between steady state and transient. I hope that also helps you basically. So as Narendra said, because of the time constants involved, transient simulations could help you in better convergence as compared to quasi-stationary.
Okay.
Yeah, please go ahead with your second question.
Means the physics section regarding to the means we are taking the channel, we are taking as a GAN as a buffer material, sir. Means when we are applying the physics section, we have to means within the GAN material we are assuming that the channel is of 5 nanometers. Means we have to apply the physics section for 5 nanometers, or we have to apply for whole GAN buffer.
So in that case, means you can define different regions within the GAN buffer itself, like region 1 near the interface, region 2, whatever you feel that means you already beforehand you don't know till what depth the carriers will be at the interface, na?
Yes, sir.
At, for example, oxide GAN interface.
Mm.
So, for example, then you can define one region for example, 100 nanometer region or 50 nanometer at the interface, and you can separately do a finer meshing in that region, and you can keep a little coarser meshing in the buffer region. You can do like that.
Okay, sir. Thank you, sir.
Sir, can I do patch photo layer with silicon?
Photo with silicon.
Insulate. Can we dope insulator with semiconductors?
Samir.
Yeah, definitely. That's a high K material, right? So you
Yes,
can.
sir.
Sorry. What? Can you repeat the question?
She's saying HFO2.
HF2.
Yeah.
You want to do what?
Dope with silicon, sir.
I don't know. I mean, it's an insulator. So
Yeah.
So you see, it's an insulator, right? And then you're trying to dope. So I don't think we have the models to support that. But then you can do that. I mean, let us say you define HF2 as semiconductor. Instead of an insulator, you define it as a semiconductor. But then what is your purpose over here?
Sir, because of negative capacitance effect, I treat my HF2 as ferro layer and I need to dope with silicon to extract more. It acts as a more ferroelectric properties.
Okay, so then, yeah. So the only way I think it can be done is defining HFO2 as a semiconductor. But then that will create problems, right? You don't want to treat HFO2 as a semiconductor, but as a dielectric, right? So maybe it is modifying some other property which you can modify, indirectly.
Where I need to modify, sir? At parameter file, sir?
No. So if you want to modify, let us say HFO2 by default it's an insulator, right? So there's a file called detexcodes.txt. So there
1 second.
you can go. Maybe quickly I can show you the manual,
Yes,
and then you can accordingly. Just one second, I'm going to share my screen now.
yes, sir.
Give me a minute. No, I'm sharing the wrong screen. Are you able to see my screen?
No, sir.
No, sir, not yet.
Naren, can you bring up the manual? For
Yes.
some reason, I'm having difficulty. Okay, I just hold on. Yeah, just bring up the manual.
Okay. So
And search for detexcodes.txt over there.
SDOS manual, na? Or
Yeah.
so let me share my screen.
So just search for detexcodes.txt. So we have three kinds of materials in Tcad, right? Insulator, semiconductor, and conductor. So metals are conductors, are by default defined as conductors, and silicon and all, they're semiconductors, right? So that is how they are defined. and all these dielectrics, yeah, they are defined as the insulators. So there you can go in and change the property of a particular material, or you can redefine a material. So let us. So can you go down a bit?
In there only.
Yeah, let us see. You know, go back. Just go back.
Yeah.
I think there was one more search result which had the section. Can you go forward?
Yeah.
Yeah. So here, yeah, this is defining dopants. You see,
Yes,
if I
sir.
say material equal to GAN, so you get the location of it here. Okay, ST root Tcad. So what is the binary path? You go to ST release. Let us say 2403, right? So if you go to lib folder, you will get a path. This datexports.txt, and then you can make a copy of this file in your directory, in your project, basically. So actually, we are going to upload a PPT on this. I mean, how to add your own materials. Of course, that includes how to modify the properties of a material also. So once you make a copy of this datexports.txt, you can redefine things for that project. So let us say you can add this silicon as a donor or whatever you want here. So you can change this material, right? You can say HFO2 here. So that means silicon will become a donor or acceptor as you want in this material. So this you can try. But I don't know how it will work out, because dopants are active only for semiconductor, right? By default, then in that case, you have to change the material type of HFO2 to semiconductor. So again, in the same file, you will see that. And then, but the problem over there is HFO2 will no longer be a dielectric, right? It will be a semiconductor. So it will solve semiconductor equations over there. So I don't know how that is going to work out, basically.
Okay, sir.
So you can give it a try, basically, and see whether you are getting the effect you want.
Okay, sir. Thank you, sir. Thank you.
I think we are going to upload a PowerPoint slide which will have the how to modify these datexports.txt, basically.
Yes, sir.
Okay.
Good afternoon, sir. Sir, this is Riya, and I have some queries, sir. Can I ask?
Yeah, please go ahead.
Okay, actually, first I would like to thank you for such a nice and helpful session for last 3 days. So my question is, okay, this part is more or less clear to me, that how to create a project and run the simulation and all those things regarding the S device and S visual part. But my question is that, suppose, sir, if I develop some model which is not which we need to incorporate with the basic semiconductor equations, like for example, mobility model that I have proposed and analytically developed. So how to invoke that thing in S device and see the performance of the device?
Naren, you want to answer that?
Actually, I just want to know any clue or the steps or procedure of invoking those kind of analytically developed, self-developed models into this particular simulator.
Yeah. Naren, you want to take that, or you want me to answer?
Yeah, you answer this.
So can you go to this PMI? Let me try to share my screen again. Okay. So now you should see my screen. Is my screen visible?
Yes, sir.
So let me share the manual. So we have a feature called PMI models. So if you go to the tutorial, so definitely it can be done. There are some limitations. I'll point those limitations. So if you go to this tutorials, right, and then yeah, so you see this section 17 PMI. Okay. So here you can include your own models.
Under a Centaurus device part, right, sir?
Yeah, I'll go from start. So if you open the tutorial, this Tcad Centaurus tutorial, you know how to open that, right? So you go to Centaurus device, and then you go here, this PMI. So here, but the thing is, I mean, you need to implement your models in C++, basically. So here you will find a description of how that is done. I mean, all the details are given here. So definitely you can incorporate your model. But one limitation is, let us say, so this is called physical model interface. Okay. So you see, I mean, there are these examples, and in C, there is a certain way of doing it. and more details are also there in the manual. So if you go to this physical model interface, right? So the limitation is that, let us say you're talking about mobility models, right? So
Yes, sir.
there are different PMIs, okay? So if you are using a PMI in which only doping dependence is enabled, then you can't have any other dependence you want. So there is a particular interface basically. So you have to select the proper PMI model. You understand, right? So let us say I think I have a model which includes electric field dependence also, right? So then maybe I use some other, this high field saturation maybe. So you need to go through all this and see which one fits you. For example, here you see, if I use, so there are many PMIs, and so this PMI, you can have electric field dependence, okay? But not doping dependence. So you see, these are the dependencies which you can implement. You can implement your own equation. But then if you want doping dependence, then you need to go to some other model like this, let us say this doping dependent model.
Okay.
And then of course,
So-
you just follow this and then you'll be able to do it. But yeah, you can not have an arbitrary dependence. You need to look at these dependencies. So each model will have some dependencies. Like this has temperature, electron density, hole density, mobility, right? So only these dependencies, this temperature, electron density, hole density dependence will be there. And then it will compute the mobility, this particular model. So that way you can do it basically. But yeah, arbitrary, anything you want, you can't do that basically. So you are constrained by the these dependencies basically. I hope I made myself
So
clear.
I need to, yes, sir, clear. But that means I need to follow the frame of their
Yes.
developed
Yes.
already predefined
Yes.
thing, kind of
Yes.
that the dependency or the parameters on which actually this mobility model depends on. So I need to
Correct.
follow that framework, and I only
Yes.
can add some new parameters onto this. Means this
Yes.
modification can be done only, right, sir?
Yeah, you can't add anything. As I said, let us say, so you are restricted in the sense you are constrained to use one of these models. So let us say I want to use this doping dependent model, but then there is no electric field dependency here, right?
No.
So only a few things are there. So I need to follow that. So I should look for a model which has all the dependencies that I want. Okay.
Yes.
If the model doesn't have the dependency, there are so many mobility models, and none of them, if they have the dependency I want, then I can't do it basically. So you'll have to think basically how to make use of these models which have been implemented.
Okay.
So it's like a function, let us say these PMIs are functions, and only certain inputs are allowed to that function. I can't have arbitrary inputs. And that is given over here. You see the dependencies, right? So you need to go through this and accordingly choose a PMI which suits you basically.
That means
I mean,
semiconductor physics supporting the parameters actually they are modeled with, so I need to follow
yes.
that only. Yes. Okay,
Yeah,
thank
that's
you,
fine.
sir.
I mean, if you don't have some exotic model, right? I mean, some which depends on something else, right? Let us say optical. I mean, I'm just giving an arbitrary example. Let us say something is changing with some other parameter which is not specified here, right? Then definitely it will not work. But yeah, for this model only this will work. Okay.
Okay, thank you.
I hope I made myself clear. So let us see this. So this doping dependent model, you need to specify. Your model should depend on temperature, electron density, hole density. Okay. So and if we go to another mobility model, again here, okay, there are two types of models again, Massetti and yeah, they have shown. So these are inbuilt models. Okay, this Massetti model, but they are showing how it can be done using this PMI interface also. Okay. So if you go to this high field saturation model, you have T and P as before, but then you have carrier temperature also dependence. And then this low field mobility also you can calculate, or a pass as an input. And even this driving force, you can use electric field as a driving force over there. And you can also use potential, electrostatic potential. So you see the inputs are varying in different models. Okay. Is it clear? Can others please mute? Mr. Biswas, can you please mute? Hello.
Rolajit Viswas, please
Someone has
mute
unmuted.
yourself.
Is not. Hello, Mr. Biswas. Is it clear? Can we
I
go to the
have
next
one question, sir.
Yeah. Yeah, please go ahead.
Prince, can we move forward? Prince.
Hello. Yes, sir. So I think someone is asking to share the link of that PDF that you shown just now. No?
Yeah, this is a manual. So all manuals are available here. I think already Narendra showed, right? I mean, you go here in the tool, you go to help section and then say manuals, right? So in manuals, and even this is a shortcut. This question mark is a shortcut to the manuals. This PDF opens up. This is a front page, and then you just click here, Centaurus device. Yeah, that's what I showed just now. So all the manuals are linked over here in this main page. So you can just click here and then go to whatever manual you want, basically. And of course, you can download it through Solnet Plus if you have account. So then you'll have it in Windows also, or you can also copy it from Linux to Windows.
Sir, there is one question from Vimal: how I can extract parameters from IV and CV curve of most device?
Naren, you want to answer or should I take that?
Yeah, so that SVG extraction. You please take this question.
Okay, so therefore that we use this extraction library. I briefly touched upon it on day one when I spoke about SVisual. So there are standard projects available. Say, you see this is the application library for 2403. So if you go to CMOS PDSOI, okay. So if you are using SVisual Tcad, you can look at PDSOI example. There is a documentation here which talks, it's a tutorial introduction to the extraction library, how to extract. So step by step extraction and visualization with Centaurus Visual, all that is explained in a tutorial fashion, step by step, okay. And somebody who wants to use Python, they can look at this CMOS characterization project. So this CMOS characterization goes through the same concepts using SVisual Python over here. So again, I'll show you the documentation of this. And again, if you look at this extraction part, so it explains in detail how to do the same thing using Python, basically, SVisual Python. And yeah, so just to explain in a very briefly. So if I look at a simple project here, I mean, any one project you can look at. This is a simplified version. So we create a curve. Basically, we are loading a file, creating data sets, creating plots, setting plot property. I briefly touched upon all this on the first day when I spoke about SVisual. And so what is the minimum you need to do even if you don't create curves? So here I'm creating IDVG curve, and then I'm creating tickle list out of this. So from this IDVG curve, right, this is the curve. So I get the variable data, and then I create two variables called VG, gate voltage and drain current values. And that is what is passed to this extraction routine. So here we are extracting VTGM. So these two are the input variables, gate voltages and drain currents, which I got in this line 44 and 45. And then the value of the threshold voltage will be stored in this VT variable, tickle variable, and it will appear as VTGM in the extraction table here. So you see this, right? This is what it appears over here, basically. So yeah, for some reason it's not, I mean, it's shown as cross, but yeah, that's what is going to appear here. Let me just check here. Yeah, so you see, right? So this project, after it runs, it appears here also. So when you vary things here, I mean, you vary your process conditions, you can see the changes in the threshold voltage and other parameters. So this PDSI project will be helpful to extract all the parameters that you need from the DC characteristic, basically. So I'll just show the PDSI project in run state. So you see this NMOS, PMOS, and then all the parameters you can see from DC, and this from IDVD, this R on capacitance parameters from CV simulations. So yeah. And of course, for detailed explanation about each procedure, it will be there in this as usual user guide. So if you go to this as usual user guide, there are these appendices. So extraction library from DC characteristics, from DC curves, how do we extract parameters is given here. I mean, there is step. I mean, all the details are there. I mean, for each procedure. And then if you want to do RF simulations and extract RF parameters, you should refer to this particular appendix. And of course, if you are interested in doing things with Python, then you can go to this help and you go to Python API documentation, and as usual, you'll open up the HTML. So Python documentation has been implemented as HTML format. So you see here, right? Documentation about as usual Python. And then of course, extraction modules are listed here. So if you click on any one of them, you'll get the details of what are the inputs, what are the outputs basically here. And there are of course helpful examples. And each of these examples, of course, has been implemented. So simple examples have been implemented in getting started. So if you go to this getting started, and if you go to SVisual right here, so both SVisual and Tcad Python examples, sorry, SVisual and Python examples are implemented. So each one of these, let us say Tcad extract, right? So this folder contains the extraction, whatever procedure is showed in the manual. Each one of them has an example here, and if you run one of them, for example, this will perform the VTGM extraction using Tcad, right? For you can see, right, there's a file for each of the extraction library procedures. And if you go to Python folder, you will have same thing for each Python extraction library method. You'll have, or function, you'll have an example here. I hope that answers the question.
So the next one is from Sreshta. Is it possible to capture the effect of 2D MOS material using multi-value band structure model?
I don't know. Naren, you know that?
Samir. No, Samir, I cannot comment on this.
Okay.
So yeah, even I don't know the answer to that question.
Another question is, sir, how we can get the parameter file for silicon docked as the SSO, and how to add the materials to our device?
Yeah, so let me bring up that slide which we are supposed to share. So yeah, this is a very common question that we get from universities. How do you add a material? So let us say the material is not available. So this slide anyway, as I said, I'll be sharing it later on. So so you need to specify the material in this data exports.txt. So first of all, you need to find out whether the material is there or not. And one way of doing it is, so you say S device and then -p and try to type the name of the material, like let us say aluminum antimonide. So if you do that, if the material exists, of course you'll get some output. Another way to check is all the supported materials. So let us go here, or maybe this one. So if I add, let us say I add S device here. So first of all, you need to check whether it is supported or not, right? By Tcad by default. So if I go to S device, and then if I right click here, and if I say edit parameters, so you'll get a list of these are the things which are supported. I mean, by supported, I mean they are defined in data exports.txt. It doesn't mean their parameter files exist. So let us say it is supported here, but parameter file. So there are two things, right? Whether the material is defined in data exports.txt and whether the material parameter file is there or not. So both cases are there. And what is the example given here? What is the material name? Can you please repeat that?
Samir.
Yeah.
That one guy had question regarding GAN also. Then he must also look whether he is using the correct parameter file for GAN or not, because he need to choose material from here. Yes.
Correct.
Yeah.
Yeah, they need to check the material parameter also. So you need to check whether it is there or not. So if it is not defined, then of course you go to datex.txt and then define it here. So this is an example. There's a project also, application library Opto FSCSI, in which I give an example of datex codes.txt. So you can define the material here in the material section. Suppose it is not defined. And then of course, if the material is not defined at all, then the parameter file will also not exist. So this talks about creating the material parameter file. I mean, you can just make a copy of the material parameter file, and you need to create your own material parameter file basically. And those details will be given in the user guide also. So you take any material parameter file and make a copy of it, and then modify it. I mean, make a local copy in the project. So both the datexcode.txt and the material parameter file should exist in the project directory. And then you will be able to work with that file basically. So if I go here, I'll just show right now how the datexcodes.txt looks. So this is the project, as I said, the example project. So you have CIS FSI. So you should know which sections you should modify also. So if I say, so you see this is the datex codes file. So from here you can define. So let us say I want to define one material, right? So I can go here and then define it. So this is my one section. Whatever material name you want to put, you can put here. And then the main thing is, okay, you can define whatever color you want. This is hexadecimal code, RGB. And then you need to say whether it is a semiconductor or an insulator or a metal. And then you can put a name. You can give a name here, right? For example, here the material name is red filter. So when you open this in SVisual, the material name will appear as red filter. Okay. So of course, you need to make a local copy of this file basically. And then of course, the next step will be to define the material parameters. And so you can just make a copy of any parameter file. So let us say you have this. So this green filter.par, okay, let us look at that because I defined it in the datex codes, right? Okay, so this green filter is the material defined in the datex codes, and then I should know what parameters I need. So this is an optical material. I need a filter to pass only green light. So that is why here in the parameter file I have only the complex refractive index section because that is what is important for optical simulations. So then to summarize, define the undefined material in datex codes.txt and then include the relevant sections in a parameter file in the same project directory basically. Okay, next question.
So can I ask a question?
Sir, the Om
Yeah.
has raised his hand. Om, are you there?
Yeah, can you hear me, sir?
Yeah, please ask your question.
Yeah, sir, I wanted to ask, like, if I perform mixed mode transient simulations for resistor NMOS inverter or for CMOS inverter, so whenever I included any quantum correction model like density gradient, it always fails to converge. But as soon as I turned it off, it converges. So can you give any insight like what I might be doing wrong?
Naren?
Right now, no, miss.
How about mesh in the channel? Because when you turn on the quantum correction model, the mesh should be very fine in the channel, right? Are you including any interface mesh?
I have like I was using the advanced transport, the nanosheet fed.
Okay. So yeah, I mean, so if you look at this, you need to have a fine mesh at the interface, right?
Okay.
So that you can check because that is where the quantum confinement effect will take into, I mean, will be important, right? So if
Yes.
you look at these transport models, and maybe you should have a look at this project because you need a fine mesh at the interface, right? Because that is where the transport takes place, and that is where you have this inversion layer formed, right? And then
Sir,
the inversion layer has a peak.
Yeah.
So that is one thing I can tell you.
So when I do the DC analysis, it works fine with the quantum confinement models. But as soon as I try to do a mixed mode, like for an inverter circuit, it always fails there. Even when I do just for a single device, I do the capacitance analysis using quantum correction models, it works. But when I try to make a circuit, it fails.
So how big is the circuit like? Is it just one
Just a simple
circuit?
resistor NMOS inverter or a simple CMOS inverter. When I try to do that, it fails.
And what is the error message you get?
It just fails to converge is after the normal message that we get. It did not converge in these many iterations. Something like that. I do not remember that.
So did you try increasing the iterations?
Yes, I did.
And how are you solving, right? Are you solving Poisson, then Poisson electron hole, and then are you following those methods of getting the initial solution? There are so many things we need to try basically, right? And what about the math section? What are your math settings? Which solver are you using? How many digits are you using? I mean, those are things you can have a look at basically. Do you need to change your solver from Pardiso? And the default solver is super. Maybe you can try with Pardiso, right?
Okay.
So even the solver settings matter a lot. So we can just give very generic answers to such questions for convergence, you know.
Sir, maybe he can raise a case for this then.
Yeah. So then it's best if you raise a case and then, so like this mixed model. So what is, so you have silicon material, I assume, right?
Yes.
So yeah, I don't know the math section here. So you see, right? Are you following these math sections here?
Yes. I am using this exact same.
Maybe you increase the digits, maybe, right? So this is like, and it's a transient simulation, you said, right?
Yes, transient.
So then you need to use this transient is equal to B. This gives better results as compared to the default. So always try to use for transient simulation this B.
Yeah, I am using this exact same math section, but yeah, it works when I'm not using the quantum correction models, but when I use them, it does not work.
Yeah, so as I said, like we'll have to check the mesh also, and so just if you raise a case, that will be
sure, sir. I'll raise a case. Thank you.
Suresh, are you there? You can ask your question.
Thank you, sir. Sir, actually, my question is regarding mixed mode simulation, sir. Nagendra has explained about AC coupled section. He's mentioned about frequency is given in the start frequency and end frequency. And also we are doing DC sweep at quasi-stationary. These DC sweep we are giving in gate terminal means then this at the AC coupled section, what we are giving that the start frequency and end frequency, at which terminal this AC signal is going to apply by the Tcad.
On the gate, on whatever bias you are, DC bias you are changing, na?
Yes.
Yeah, on that as small signal will be superimposed.
Okay. Oh, superimposed in the same terminal, which means we are doing
ramping
DC sweep for gate terminal, then the same AC signal is applied on the gate terminal itself.
Yeah, it just means for each DC bias point, it just superimposes a small signal AC and calculates the admittance.
Okay. Sir, as well as if for AC means the signal will have some amplitude component also now, sir. Sir, what is the amplitude component for this Tcad giving this? Only we are defining 1 megahertz or 1 gigahertz like that.
So by small signal itself, by the definition itself, we mean that whatever the sinusoid you are providing as a superimposition.
Okay.
So it should not affect the biasing. So it's like that. Yeah, so I don't know the exact value, but it might be considering 5 millivolt or something. I will have to look, but it should be small such that means it should not affect your DC biasing.
Okay, sir. Sir, then if I want to use a small FET device, it may be any type of transistor. Now I want to short any two of the terminal means whether I can do it in the mixed mode simulation. If I want to short gate and drain, or source and drain means whether I can do it in mixed mode.
So in the examples which we showed you, so you are actually shorting the substrate and source terminals, na? Means you just connect them to the nodes, to the circuit node, ground nodes.
That's enough, sir.
Yeah.
Okay, sir. Sir, if I want to design a voltage control oscillator circuit with the help of any FET transistor, what are the things I have to consider, sir, to avoid some major conversion issues and all, like by incorporating LC circuit or RC tuning circuit with the FET transistor. I want to design one voltage control oscillator. What are the things I have to consider?
So I think means regarding this oscillator, I think Samir is the better person to.
Okay, sir. Okay.
No,
Sir.
even I don't know about that. Sushant? Sushant has also joined, it seems, so maybe he can answer. Sushant, are you there? Can someone unmute Sushant? Naren, are you able to unmute?
Sushant.
Yeah, he
Sushant,
has just
sir,
joined.
you can. Yeah, you can.
So what
unmute
was the
now.
question? Can you repeat? I didn't get it.
Sushant, actually, my question is, I want to design a voltage control oscillator circuit with the help of FET transistor. I'm going to incorporate any LC tuning circuit or RC tuning circuit. What are the major things I have to consider to avoid some major conversion issues, especially
For any
in mixed
application?
mode simulation?
Yeah. I mean, I don't have, because I have not simulated on my own, but so this, I mean, you have to get started, and once you, and in their manuals, like for different models, there are like
Okay.
convergence criterions are given, and best known practices are also given, so that can help you to do that. So don't have to fear it and plan it so much in advance. You can just start it and then see for yourself. Yeah.
Okay. There is any limitation number of components what we are incorporating using mixed mode simulation? Whether these many number of transistors only we can incorporate like that? Any limitation?
No, there
for
is no
doing?
limitation. But as Narendra might have pointed out, but if more the number of transistors, more the coupled equations will be solved, so the simulation will become slower. But as such, there is no limitation, so you can try it out.
Yeah, I mean,
Sure.
you should have a
Okay.
memory. I mean, enough memory, right? The more the
Yeah.
more the elements are there, the more memory you need, right? Because more the data has to be saved. So maybe 6 transistors, 8 transistors ideally, but more than that, it becomes really, it takes a huge amount of time otherwise to simulate basically.
Okay, Samir. Thank you. Thank you.
And maybe he can start with some built-in models first before introducing our physical models from LTY. Means otherwise, as some other guy was saying, convergence issues, and so maybe you start with
Yes.
some start with some built-in models so that it runs smoothly. Then you can incorporate whatever devices you are making.
Sure. Okay. I will look into it. Thank you.
Tejaswini Sahu, are you there? If you are there, you can ask your question.
There was one question regarding 2D simulation, incorporating 2D material in 3D devices. Maybe Sushant can answer if they can ask again about that.
What is the question?
I don't remember. Somebody was asking about incorporating 2D material in 3D devices, I think, in MOSFET.
She was referring something like multi-valley kind of thing for 2D.
Multi-valley model, basically. Or you can just raise a support query and we'll answer through that. Any other questions are there?
So germanium pocket inside the pin channel, then it shows error like check undefined models or use math to skip this. So what should we do to use it?
Yeah, I think I can take that. So if you look at the manual and if you, so you need to define basic set of models. Okay. And that is given in the manual. Like, so if you say, so the word you use is check undefined model. I'm sharing my screen right now. Check. So those minimum set of models you need to specify. So you see here, right, for each material type, what are the minimum models you need to specify. That's what is given here. For example, if it's an insulator, you need to have epsilon kappa radiative, epsilon kappa, and then refractive index and shorting. So this will give you what models you need basically. Okay, and then you can either define them or you have an option of turning it off. So you can, if you know what you are doing basically, then this checking you can turn it off by using minus check undefined models in your math section. So either way will work for you basically.
Hello.
Yeah, you can ask your question. Yeah.
Yes, sir. Actually, I'm Tejaswini from NIT Rourkela. Sir, actually, hello, am I audible?
Yeah,
Yes.
audible.
Sir, actually, my question is I'm doing on ferroelectric basically, and I'm using a silicon doped HFO2. So which is normally called HSO. So, sir, I'm not able to, derive the parameter exactly for HSO. So, is it possible to get the parameter file, or otherwise, how we can, manually define that material?
So I think, were you there? I had answered this question some time back, right?
Yeah, sir, but also you said we need to convert that HFO2 to semiconductor.
No, yeah. So it all depends on what you want to do, right? Because
Yeah, sir,
there the drawback is it will solve the semiconductor transport equations in HFO2, which maybe you don't want, right? So maybe you need to do literature survey and then come up with the material parameters, right? Because we don't know the material parameters. I think you guys are better at doing literature survey, right? So if you come up, if you know the material parameters, then you can implement those material parameters. Maybe, so what is the effect of doping silicon, right? If you dope HFO2 with silicon, what is it modifying? So those parameters you can update.
Yeah, actually, sir, I want to use it as a ferroelectric basically, because HFO2 also acts as a ferroelectric, but to enhance its property, we can dope it with zirconium or silicon to make it to SZO or HSO. So that's why, yeah, so that's what I'm trying to do to convert it to ferroelectric basically.
Okay. Yeah, so I don't have experience with ferroelectrics, but yeah, we have projects in our getting started library. So if you look at the manual or the library,
Yes, sir,
there's a chapter on.
Yes, sir, I have checked, but it's basically for ferroelectric FAT in memory applications.
Yes.
In this getting started, I have checked. Yeah. But sir,
you're right.
Sir, is it possible to get any example in ferroelectric capacitor, like metal ferroelectric metal structure?
I mean, you can build your own example, right? That should not be very difficult. Metal ferroelectric. I mean, basically, you put a dielectric.
So Tejaswini,
Sushant, you want to answer?
Yeah, sure.
Yes, sir.
Tejaswini, like whenever some material is being doped or like whatever properties are being changed, right?
Yes,
so you
sir.
should be aware of like what is the impact of that. Like when you dope the HFO2 with silicon, personally I don't know. But if so, for example, it changes the dielectric constant. So then just for an example, or if it changes the polarization charge or whatever.
Yeah, so it changes the remnant polarization, the coercive field, the static saturation polarization, all those things.
Yes.
PSP.
So these properties should be defined in the materials file. So you can go and change that, and then the material represents the material you want to
Sir, actually, that is I'm not getting.
What do you mean by not getting?
And you need to build a CV example on your own then, right? I mean, you can just create your own the structure. And then the way CV has been done for other materials, you can try doing here, right? Because this ferroelectric chapter talks about how to do small signal analysis, right? On these materials.
Yes.
It's mentioned in the ferroelectric chapter actually, how to do AC simulations.
Yeah, basically we give the ramp pulses, triangular pulses to it for the hysteresis P curve. So that is my target actually. But sir, the parameter values I'm not getting from for the silicon doped HFO2.
Yeah, we can't help you with that basically. So there's not there. I'm sure there will be literature online, right? Maybe IEEE or
So
somebody has it,
see,
right?
so you have to understand there's
Yeah.
different components of simulation tool, like as Narendra explained very nicely.
Yeah.
So like how do we incorporate like parameter file and all, and what is the functionality of that? And if you're aware of those things, then
Yeah.
these
I'm aware,
questions
sir. I'm aware.
yeah, so then these questions you should be able to answer, because if you know where is the parameter file and then how you edit it and what is the impact of different parameter, then you know
Yeah.
how, then you can do that. I mean, it doesn't look like a very big problem to me also.
Yeah, sir, I understand, but sir, actually, I have been trying it for so many days, but still, I'm not getting the P curve for HSO. As for HFO2, I'm getting the hysteresis curve, but while I'm
That
changing
means
the
you're not
parameter.
changing the right parameter. That means we can just say that, right?
Okay, okay. Sir, is it possible to define our own, like Samir sir said, to make our own material with HFO2
Yes.
with.
You can do that, yeah.
Yeah. So that's
Okay.
what. So you define a new material, call it whatever
Yeah.
you want, right? Let us say HSO, you call it, right?
Yeah.
I mean, here in this case it is HSO, right? So you define it in
Yes.
netexcode.txt, but then after you define it, you need to define your own material parameter file, and for
Yeah.
that, as Sushant said, you should know the effect of that doping, right, on the material parameters, and
Yeah.
then you need to get the values from literature. We don't have those values actually, right?
No, sir.
We don't do that
Yeah,
kind of
yeah,
research,
yes, sir.
right? So
Yes, sir.
so then you should know what. So it's a dielectric. So you should. I just showed the model. I mean, just take undefined models, right? So there,
Yeah.
what are the minimum set of models you need for simulating this thing, right? Insulator is given over there, huh?
Yeah,
And
sir.
then you
What is
can.
that syntax for JEdit detex code? What is, sir? Can I know once again?
Oh, that is JEdit basically. So
JEdit. Okay.
we have an editor called JEdit.
Okay, sir. Actually, sir, I searched for that capacitor, ferroelectric capacitor, and in that tutor training you said, but sir, we don't have that S device wizard in our college. So how
No.
to do?
You have it. I mean, just now Narendra showed, right? So
Yeah,
you're talking about Wizard or are you talking about JEdit now? Because both are
wizard,
different, right?
wizard, sir. Wizard, in that wizard, it is written that ferroelectric capacitor examples are there. So, sir, but in Nitroarcola, we don't have that wizard, S device wizard.
Which version are you using?
Version, sir, I'm not 22 version.
Yeah, so 22, I think we already, so earlier we were distributing the Wizard as a downloadable file, but now, I mean, 22 or 21 onwards, it is part
Yeah,
of the tools. So if you, the way Narendra showed, right? If you add
yeah.
S device to your project tool flow, you right click, then
Uh,
automatically you should get Wizard. Okay. And if that is
okay.
not happening, that means you have an older version. And if you have an older version, you can search on Solnet Plus. Do you have access to Solnet Plus?
Sir, we have, but actually we are not allowed to access it, the
Yeah.
solvent
So,
actually.
so you get in touch with whoever is there. I mean, you're in
Uh,
charge, and then ask them
yes.
to. So there you can download Wizard. But I'm
Okay.
sure with 2022, you will have access to SDW.
Okay, sir. Okay,
So
sir.
just try to add it the way Narendra showed. I mean, later on, you can even look at the slides, right? Because we'll be uploading these slides,
Yes, sir.
right?
Yes,
So
sir. Okay.
definitely you'll have access. Okay,
Okay, sir. Thank you so much, sir.
sure.
Samir, there is a question that if we have zinc oxide material parameter
Pardon?
there is a question that if we have zinc oxide material parameter, so have you shown, or Narendra has shown, like how they can figure out what are the parameters available in this device material database?
I showed just now.
Okay.
So
I did not cover in this presentation, Sushant.
yeah. So anyway, I'll be sending this presentation also, right, Sushant?
Okay.
Where how to add new materials. So in that I'll include first how to check whether that material is there or not. And then if it is not there, how to add it in datexcores.txt. You have to define the material and then you have to check whether material parameters are there or not, right? Definitely, if material is not there, material parameter file will not be available. So two steps are there: add it in datexcores.txt, define a new material parameter file in the project directory. And if the material is defined for, in many cases, we don't have good parameters defined for those materials. So in any case, then, so for some exotic materials, you need to again add your own material parameters, basically.
Okay.
So for many cases, we don't have good parameters. And if you don't do that, if you don't define your own material parameters, then if you use silicon parameters, which are definitely not good, let us say for compound semiconductors or any other different materials, which are totally different from silicon. Any other questions are there?
There is one
hello,
more
sir.
question. Can we form 1 kb SRAM cell from transistor design and Tcad?
Hello.
Sushant? Sushant, are you there?
Sir is mute, I think.
Sorry, I went on mute. I was speaking. So 1 kV SRAM cell will have like a lot of transistors. Like one SRAM cell has 6 transistors, and 1 kb will have like I think many of them, I don't know, 6,000 or whatever. So then to simulate that using Tcad will be like you will be solving the equations for all of them, like that will become like very long simulation. So we would suggest to use CMI, compact model interface, to do that, or circuit simulation to do that. And you can maybe make the compact model of the individual transistor and then use it. That would be the recommendation. But it's possible to do it somewhere or the other. Yeah. Make sense, Amir?
Yeah.
There's a question, Samir. What if the syntax is not available to define a material property? That means if the, let's say, screening length of a metal, the guy is saying, and so that means the physics is not incorporated, then I think recommendation is to make PMIs, isn't it, Samir?
Yeah, but as I said, PMI depends, right? I mean, what are the dependencies you're looking for? And the PMI should exist for that property, right? So we have standard set of PMIs, mobility. I mean, whatever is there in the transport equation, we have PMIs for those parameters, right? Like mobility, generation recombination rates. And that too, we have restriction on the dependencies. So yeah, they need to look at that and then take a decision.
Ashutosh is asking, I think for a long time, this quantum confinement.
Can you unmute yourself, Ashutosh, and ask the question? I mean, what is the question here?
Ashutosh, you can unmute and you can ask question. Ashutosh, are you there?
So Manish also has a question. I have a question regarding gallium oxide MOSFET related file in Tcad.
Yeah.
So ask your question, Manish.
Sushant, there is a project with gallium oxide file, right? I don't remember the project name. You remember we had a case.
Hello.
Yeah, Manish, you can ask your question.
Sir. Sir, actually, I am working on gallium oxide MOSFET devices. So I am from Anachal Aukela. So actually, the project that is in the CentOS Tcad under the power file, there is a gallium oxide project. Sir, that's the paper, the GREADME PDF that is given there. There is a different material doping, and that the project file that is a structure as a device SD file, the code is different for doping. It has doped with arsenic. In the paper, it is given that it is doped with silicon or astatine.
Which project are you talking about?
Sir, about gallium oxide MOSFET and
No,
capacitors.
I mean, you are referring to some project in our application library?
Yes, sir. Yes, sir. Yes, sir. Gallium oxide.
What is the project?
In, sir,
gallium
in
oxide
power
MOSFET. I know, gallium
Yes.
oxide MOSCAP
Yes, sir.
MOSFET. That's what you are referring to, right?
Yes, yes, sir. Yes, sir. Yes, sir. Yes, sir.
So what is your question regarding this? Can you please repeat?
Sir, actually,
I'll just
the
bring up.
doping-
I'll just bring up the. I'm sharing my screen now.
Okay. Okay.
So
Sir.
it should be. You can see my screen, right? So yeah, this is the project you're referring
Yes.
to, right? Simulation of.
Yes, sir. Yes, sir. Yes, sir.
So what is the question now? The
Sir, my
doping
question
mentioned
is-
in the dopants mentioned here are different from what is there in the
Huh.
command file.
Paper, sir. No, no, sir. Command file is itself same, but the paper which
Okay.
is referred in this file, GREADME, that the reference paper, actually, sir, in beta gallium oxide type of devices, there's a doping of silicon or tin material. But in this device, it is doped with arsenic.
Mm-hmm. Okay.
Yes, sir.
Yeah, so if you know as we discussed earlier, if you know the material parameters for your case, then you can modify your files, right? The parameter file.
Actually, sir, when we go into the constant profile placement and choose the doping material, sir, there is one material called silicon active concentration.
Yes.
With doped with silicon active concentration, and there is one other material which is named as N-silicon active concentration. So, sir, there is a difference between silicon active concentration and N-silicon active concentration doping materials which are available inside this software.
Yeah. So let us say you are defining a new material, right? So then you can define in data codes what is the effect of that. Is it N-type dopant or P-type dopant?
No, sir. These materials, sir, these doping materials are itself available inside the file when we go via constant profile placement.
So, so when we say that N silicon, so it means that it is doping silicon as N-type dopant there.
Yeah. So if you are introducing silicon in a material, and if you use N-silicon, that means silicon is acting as an N-type dopant, right? Because in some materials like gallium arsenide, it's an amphoteric dopant, silicon, right? It can be either N-type or P-type.
Yes, sir, yes.
So to take into account, I think those effects you can choose N or P.
Okay.
Does that answer your question?
Yes, sir. Thank you, sir.
Okay, Ashutosh, maybe you can ask your question now.
Can you unmute him, Ashutosh?
Sir, all are unmuted. They can ask questions by unmuting themselves. So, Ashutosh, are you there?
Hello.
Yes, please go ahead. Sir, Ashutosh has typed one question. Basically, in TFET, the dimensions are less than 10 nanometer. How do one apply quantum confinement model? In Silvaco, you have Schrodinger poison, but it is not in the Synopsys tool.
So we have quantum confinement model, na?
Yeah, we have Schrodinger Poisson solver also.
Yeah,
so if you go to the quantization chapter 14, you have this 1D Schrodinger equation. Okay. So definitely, if you go through the manual, you'll see that. Okay, so it is specifically chapter 14, 1D Schrodinger equation.
And density gradient is the model which is used usually. I mean, because
to capture those effects, yes, confinement effects.
And you can calibrate it using Poisson-Schrodinger, which is also there in Synopsys.
Yeah. So please look at chapter 14, 1D Schrodinger equation section.
Hello, am I audible?
Yeah.
Sir, I have a question. Actually, I want to incorporate screening length for metal, but in load bar file of, let us say, aluminium, I can only change the bar function value. So how to incorporate screening length or some other property for any particular material?
Can you please repeat the question? It was not very audible.
Yes, actually, I want to incorporate screening length for the metal. It can be any metal. In load bar file.
Screening. So
So
yeah, if it is,
I
I don't think screening is defined in our solvers. I mean, in our simulator. Yeah, I don't see that. Have you checked the manual?
Yeah, screening length is not there in the manual.
But can we do it indirectly? I mean, what is the effect of screening length parameter, and then try to work around it, sort of. So are you talking about device length basically?
Yes, sir.
I mean, are you talking about device length basically, or is it different from screening?
Or is it
A kind of
screening?
device length, yeah.
Is it the charge screening in a semiconductor, or is it somewhere else you're talking about?
Sir, it's
Because
a device length.
there is a screening parameter which you can use in the mobility section.
That one, sir. Screening length means the length up to which your electric field will become.
1 by, right?
Yeah. Device length.
Yeah. So that is in metal. You want which material you want to define?
Yeah, in metal.
Metal, right?
Let us say
Yeah,
for
so-
aluminum or titanium nitride or any other metal.
Yeah. So this, whatever Sushant is saying, that is in semiconductor, right? Sushant, that is in mobility
Yes,
model.
yes, sir. That is in.
Yeah.
Semiconductor.
No, I don't see how you can do that. And then, as I said, I don't know what is the effect of that in your simulation, right? So maybe you can work around it, right? So we showed you the equations which are being solved and the parameters
Yes,
which are there. Somehow can we? So for metals, we are solving this metal transport equation, J is equal to sigma E. I mean, in short, basically. So somehow can we change things over there in the material parameter file of metals? Indirectly, we have to think about it if it is not available, basically.
Okay, sir. Got it. One more thing, sir. If I want to change the temperature, for lattice temperature, I know the syntax for, let us say, for silicon. But if I want to change the temperature for stack, let us say MFM or MFM, any stack, most cap, something. So can we do that? Can we change the ambient temperature for any device in Tcad?
Can you please repeat? I did not get the question.
Sir, my question is, if I want to change lattice temperature, let us say for silicon, I can do this because this is given in manual, how to change lattice temperature.
Yeah. I mean, in the physics section, you just say temperature is equal to, is that what you're asking? I mean, in physics section,
yes,
anybody,
we can do that.
it doesn't matter. Anybody.
But for
So
complete stack, let us say for
Yeah.
most cap.
Yeah. So if you say in physics, don't use material specific physics, okay? If you want to change the temperature of the entire device, right, and that is how it should be done. So you specify in the physics section temperature is equal to 300K. I mean, 300K is the default. So you can specify whatever temperature you want in the global physics section. Okay.
Okay, you mean global physics section? Okay,
Yes,
okay.
not in the material specific.
Okay.
So I don't know what will happen if you change temperature in the material specific section, but definitely you should put in the global physics section. Entire
Actually,
device.
sir, I was changing the temperature for HFO2 for one of the upside in my stack, but I was not getting the impact of temperature. So that's why.
Okay. Yeah, please try it in the global physics section.
Okay, sir. Okay, I'll try. Thank you, sir.
So any other questions from the audience? So Ashutosh is you can either raise a ticket at Solnet or in the chat I have put in a link there. Our Chipin team can also help you. So both ways for all the participants, if they feel they need some help or they have some query or some issue, so they can easily either raise a ticket on the Solnet or they can raise a ticket on the chipin.cdacv.in. And if you have some query, now is the time. You can unmute yourself and you can ask the presenters any questions.
So one more thing, sometimes we get installation related queries. So what should they do, right? I mean, it seems there are some videos on installation of Tcad software, right? Does everyone know how to access those videos?
Sir, we already have put in the videos as well as the documents on the our CDAC cloud. And
Okay.
if the query comes to us, we can directly point them towards those documents only. But
Okay.
sometimes if they directly go to the Solnet, then we can't track the Solnet.
Yeah. So what should we tell them? Like whom should they contact? So sometimes we have
They
those
should
cases,
contact
you
the
know.
Chipin team. I think in the chat I have put in a
Yes, I see that.
chipin.cdacv.in. A link is there on that. If they raise a query, raise a ticket, they can or they can parallelly call also at our CDAC Bangalore center.
Okay. Yeah, that is helpful for us because we get support cases and we need to answer those cases. So yeah, that's what we'll do then. Okay.
So any other query from the participants? Okay, if there is no query, so thank you, sir, for conducting this wonderful session. So I hope it was very wonderful and very informative for all the participants. Thank you, sir.
Yes. And one more thing, we'll be uploading some more files by tonight. Especially, I didn't upload the as usual ones, so then everyone can maybe download those files tomorrow. So I hope everyone knows how to download those files. Yeah. So
Okay,
thank you for organizing this workshop. It was, I mean, we also enjoyed presenting. So thanks a lot to everyone who attended basically. So.
Okay, sir. Thanks a lot. So we'll now conclude the session.
Okay,
Thanks to all the participants for attending, and thanks to all the presenters for conducting this wonderful session. Thank you all. If you have any query, please raise a ticket on chipin.cdacv.in.